This is something that's going to change the possible when it comes to human spaceflight.
This is Paul Sutter. He's a theoretical cosmologist and a NASA advisor, AKA he's a space expert, okay? And today he's gonna talk to us about time travel, whether it's theoretically possible to move forward or backward in our timeline.
Great Scott.
And the role that black holes might play as potential wormholes, as an actual portal to facilitate effective time travel.
Wormholes aren't just shortcuts in space. If you have a wormhole, you have a time machine.
And how the concept of the multiverse could mean not just traveling forward or backwards through time, but laterally into an entirely different universe. A universe that looks just like ours, where everything is the exact same, but maybe one thing is changed.
The whole planet's on the come! Go, go, go!
This episode is absolutely fascinating. Paul is a brilliant guy. He's incredibly kind and charming and explains all these concepts really, really well. So if you are interested in astrophysics, the concept of space and the universe, this is the episode for you. So sit back, relax, and welcome to camp. Dr. Paul Sutter.
Hey.
How are you?
It's been too long.
I know. Welcome back. Thank you so much for joining me. I'm very excited to chat with you again. The audience loved the last conversation.
I loved the last conversation. It really was a very, very fun conversation. I loved how wide-ranging it was.
Yeah. We're going to do the same thing today. But now you're a New York Times published author.
There is that.
What has happened?
What has happened?
Is this, I don't want to take too much credit, okay? It's not me.
Well, you know, it's funny because the New York Times reached out to me and they said, hey, you were on that Brooklyn guy's podcast, right?
Yeah.
That's how they refer to you. You know.
Wait, no, they did not bring me up.
They did not.
Okay,
damn, no, sorry.
damn.
Sorry.
I was about to be so excited. I was like, dude, the Times is talking about me? That's wild.
But NASA headquarters, when they asked me to serve on an advisory board, they also did not reference
Damn it.
you. I'm sorry.
Come on,
I'm
Paul.
sorry. I'm just teasing
Bring
you.
me up. You got to slide me in there. Be like, hey, NASA, I know you guys are doing a lot of work, okay?
We're very busy.
But
yeah,
check out this pod.
check out this podcast.
But yeah, that's awesome. NASA advisory board.
Yes, I serve on the advisory board for a program in NASA called NIAC, because we love our acronyms.
Hell yeah.
This is NASA's Innovative Advanced Concepts Program. It is so magical. I love this program. It is like getting a front row seat to the future because this is the program that NASA uses to try out brand new ideas that aren't going to propel us in the next few years or change something or make some minor advance. This is something that's going to change the possible when it comes to human spaceflight and robotic spaceflight, where we're looking at 10 years down the road, 20 years down the road of what could we do differently. If this is a program that asks, take the realm of possible given our current technological levels and how that might progress in the next 10 years. What's something more we could do? What's something we could change? How can we change the discussion of what is possible in the next generation of spaceflight? So these are radical ideas. These are sci-fi ideas. These are crazy ideas that are probably wrong, but they're plausible. They're all grounded in physics. They're all grounded in realistic engineering. They're grounded in real biology and chemistry and everything else we need to know. So they're plausible and they're worth poking at just a little bit, just to see if this could be a real thing that we could actually develop in the next generation.
So the research phase, is this something we would call like low cost, high impact?
Exactly. This is very low cost to give you some sense of scale. And in fact, this program, NIAC, is open to anyone. You do not have to be a university researcher. You do not have to be a NASA employee. You do not have to work in industry. You can be in your studio in Brooklyn, and you can come up with a cool idea and you can propose it to this program.
Oh,
It's
wow.
open to everyone. There are 3 phases. Phase 1 proposals last for 9 months, and the funding is around $600,000 so that you can pay for some graduate students or some assistants. You can flesh it out. And the idea is, we know we're not going to generate an actual piece of working technology with this kind of a small budget and short time frame. The goal is to dig deeper into an idea, to see if it works, to see if it makes sense to continue developing, or for you to run into a problem and say, you know what, this idea turns out it's not a good idea after all. We do run into some fundamental roadblock. And if if it is a good idea, if it is worth pursuing, then you can apply for phase 2, which is, I believe, for a year, and it's around $1 million. And then phase 3 is for a 2-year program for $3 million.
Wow.
And in terms of research grants, these are tiny, especially aerospace research grants.
Right.
These are just proofs of concepts. These are just ideas generated. If it is successful, if it shows promise, then it gets passed from this program, from NIAC, to other NASA offices that can provide further development to actually create a working mission out of this. So an example, a success story of this program is the Ingenuity helicopter on Mars. You know, that tiny little quadcopter that went along with the rover and it did like dozens of test flights on Mars. That didn't come from NIAC directly because NIAC didn't exist at the time, but the program that evolved into NIAC, the predecessor of NIAC, did create the idea behind, hey, maybe a helicopter on another planet will be really useful for remote sensing, for gathering samples, for moving very quickly. And now it's a real thing on a real mission, and now it will be a part of many more missions to come.
Oh, wow. And so the things that you're looking at within NIAC now, can you share what some of those early phase, like theoretical ones are? Maybe some of the grounded ones, but also what is like the most insane one?
Interstellar flight. Like, how do we actually develop a reasonable propulsion system for going to another star? There's this wonderful research based on using fungi to build Martian habitats.
Whoa.
Where the idea is bringing a whole structure to Mars is going to be insane. We can't do that. So instead, how about you bring a flexible foldable mesh with you in a little vat of a fungus, a special fungus. And this fungus is adapted to the conditions on Mars, the harsh conditions on Mars, but is genetically adapted to survive there. Then you go to Mars, you unfold your mesh, and then you plant the fungus, or do whatever you do to fungus to get them started. And then you feed them. And you give them water, nutrients, and then they grow to fill out the lattice. And then you have a sealable structure that you can pressurize and exist in on Mars.
Wow, this is literally The Martian.
The Martian, but even better, where we're growing the habitats instead of just trying to assemble them or build them or bring them.
And the nature of like fungal growth on Mars, like I don't know everything that goes into, like spore reproduction, but what is happening on Mars that you're able to do this fungal reproduction? Like how is that done? Like going from phase 1 to phase 2. Alrighty, don't skip forward, guys, because I am on the road, world's fastest ad read, coming at you. I'm going to be in Buffalo, Raleigh, Poughkeepsie, Portland, Oregon, Fort Worth, Texas, Austin, Texas, Stanford, Philly, Levittown, Chandler, Arizona, San Diego. I'm also going to be adding Toronto, Montreal, as well as Washington, D.C., and a bunch of other dates. Dates are in the description, also in probably the comments of this episode. Go see me on the road. Come hang out. I'll be hanging out with everyone after the show. Come shake my hand. Call me an idiot. Whatever you want to do, I will be there. Additionally, I will be doing my 1 hour of stand-up comedy. I'm very proud of this hour. I'm really excited to share it with you guys, and it would mean the world if everyone could come on out. And what do you wear to a show on the road? That's a great question. You can go to campgoods.co. That's right. We got merch. We got camp merch. We got hats, hoodies, t-shirts. A lot of stuff is out of stock. Things have been selling like hotcakes, but we're going to be restocking everything in all the sizes. So you can go there right now, get all the merch, get all the coolest clothing in the podcast game. We're going to be updating that site regularly. And if you come out to a show, I'd love to see you sporting some of the threads that we got up online. I'll see you guys there. Let's get back to the show.
So in terms of these phases for NIAC, even a phase 3 is not an actual mission. Like we're not actually putting something on Mars. That takes way more than 3 years, and it takes way more than $2 million. Space exploration is very long, very hard, and honestly very expensive. There's no cheap, easy way to do it. So even phase 3, it's still proofs of concept. It's doing stuff in a lab. It's like, can we modify organisms in the lab that get them to survive in Mars-like environments or simulated Mars environments in a laboratory? Can we get them to grow structures? When they grow structures, how sealable are these structures? Can they maintain air pressure within them? them? Can they maintain their temperature? How well do they survive against, say, bombardment of UV radiation? Like all the questions you might ask to challenge an idea. If someone says like, hey, I'm going to use mushrooms to grow structures on the surface of Mars. And you might say, okay, sounds crazy, but have you thought about this? 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 And the point of a NIAC program is to be able to answer all of those questions. Say, yes, I've thought about this. Here's the challenges. Oh, I've thought about that. Here's what we'll need to develop. Oh, I've thought about that. Here's what we'll have to mitigate in terms of risk to make this successful. And you check off all of those potential questions. And then if it's still promising, you keep moving ahead.
And what would be the overall benefit, let's say in 10 or 20 years, if you're able to create this, fungal lattice structure on Mars?
Oh, great question. By the way, Lynn Rothschild is the leader of this program. You should absolutely have her on your show. She's amazing. She does so much cool work when it comes to biology, the intersection of biology and space. And the whole point of this is, again, to change the possible, to change what we can potentially do in the next generation of spaceflight. Right now, when it comes to Mars colonization, even Mars missions, habitats are a big problem. Just walls and a roof that can keep the dust out, that can keep air inside reasonably well. We do not have the technology to have a habitat on Mars, to actually build it here on Earth, fold it up inside of a rocket, and get it to Mars along with a crew of humans. We simply don't. So we need to come up with smarter ways, more efficient ways of building structures on Mars if we want to be serious about Mars exploration. And this is a potential way to do it, a very creative, ingenious solution to a problem that changes the discussion of what we could do a generation from now.
Oh, wow. So is the idea with the fungi, is this like, okay, we can create a food source? Is this so that we can test out the structures themselves, or is it both?
Right now, it's for this particular project, it's just based on structures. I don't think these are edible fungi. I don't think they deliver a lot of nutrients.
No psilocybin in those?
No.
Dude, tripping on Mars would be crazy.
I don't. If you want to, sure, go ahead. Have fun, and please just do it outside the habitat.
Yeah.
Right now, as far as I'm aware, for this particular example, it's just based on changing structure. There are a lot of projects looking at food sources and efficient ways to grow food on asteroids, on the moon, on Mars. There are different methods of propulsion that we could potentially use, like fusion or fission-based propulsion methods. There's so much cool stuff in astronomy. There's a proposed mission or a mission design to send a spacecraft to, I think it's around 3 times further than the distance to Pluto, and have it sitting way out at the sun, or far away from the sun. And the sun, the gravity of the sun, can bend the path of light, just like a lens does. This is general relativity. And it bends the light from distant sources to a focal point. So if you sit at the focal point, it's like having a telescope lens the width of the sun. It's by far the most powerful telescope you can ever imagine in the solar system. And this proposed mission sends a fleet of spacecraft out to this focal point, which sits very, very far away, captures the light at that focal point. And if it's aligned just right, if you're looking at, say, a distant exoplanet, a planet sitting around another star, you can build a map of it down to around 100-kilometer resolution, which means if there's life on that planet, you're going to spot it. Like, you will literally see forests on that planet. If there are alien cities on you'll see the alien cities. Unmistakable signs of life and unmistakable, unmatched ability to study another world outside of the solar system, where no telescope that we have now, that we'll have in the next round of space telescopes, in the round after that, the round after that, the round after that, there is absolutely no way that we could ever engineer a more powerful telescope than what the sun's gravity already does.
Wow.
So that's NIAC. This changes the conversation of what's possible in the next generation.
Wow. So just for perspective, the current most powerful telescope is the James Swift?
The James Webb.
James Webb.
Yeah.
James Webb.
The James Webb is currently the most powerful space-based telescope. It has a mirror about 18 feet across, about 6 meters across, which is very large for a space-based telescope. It was so big that it couldn't fit in a rocket housing. It had to be folded up very cleverly to be able to fit inside of a rocket and then deployed into space. We do have ground-based telescopes that are far larger. We have a telescope being built right now called the 30-meter telescope, which is 30 meters across. It's a very appropriate name. And we do have plans after that in the next, say, 20 to 30 years to go even larger on the ground. There is a successor to the James Webb that's currently in its design phase. It's called the Habitable Worlds Observatory. It will be larger than the James Webb, but not by much. And to contrast that with using the gravity of the sun to image a planet, if we were to build this telescope that flies out all the way, 3 times more distant than the orbit of Pluto, and take advantage of the sun's gravity, you can get, for nearby exoplanets, you can get around 100-kilometer resolution. For the Habitable Worlds Observatory, the successor to the James Webb, which is going to target exoplanets, it's going to hunt for life, it will have resolution where an entire planet fits in 1 pixel.
Wow.
That's what it can do, is 1 pixel for an entire planet.
Okay. Which, I mean, is impressive.
It's impressive.
But you're not going to know if there's a forest or life.
We won't know if there's forest. We can potentially know if there's life. And that's not from that pixel itself, but from the spectrum of the light that comes from that planet. Where if you change the abundance of molecules, if you change what the atmosphere is made of, if you put in, say, a bunch of oxygen in an atmosphere, a byproduct of photosynthesis, if you put a whole bunch of oxygen in an atmosphere, that changes the light coming from that planet. And the Habitable Worlds Observatory, even though it won't deliver great pictures, it will deliver very, very excellent spectra. So it will be able to tell us what molecules, what elements are in the atmospheres of different planets.
Okay.
And it's through that we will be hunting for signs of life.
So those would be key indicators.
Key indicators, that we have a word for it. It's called biosignatures, signatures of life based on the chemicals in an atmosphere.
Now, this new concept coming out of NIAC, though, of actually bending the light to create this focal point, if the current, like Earth observatories are giving us an exoplanet at 1 pixel, what could this give us an exoplanet in terms of resolution? You said 1 kilometer.
Like thousands of pixels across.
Wow.
Like an actual picture that you could hang in here of a planet orbiting another star.
Yeah, so that would be, I mean, a multiple in terms of resolution of 20, 30?
Huge, more than that. We're talking, I forget the exact numbers off the top of my head, but it's over a factor of 1,000,000 times better than the Habitable Worlds Observatory.
Now, in terms of bending light, I understand, like, black holes will do a version of this where, like, light will be bent.
Yeah.
How is this far off telescope, how is it able to bend the light in this way?
Great question. The telescope itself isn't doing the bending of the light. It's the sun that's doing the bending of the light. It's the sun's gravity that is bending light. The sun is already doing it, just like a black hole does, but not as strongly, because the sun doesn't have as much gravity at its surface. But it does bend light just a little. And then it sends that light to a distant focal point that's something like 550 times the distance from the sun to the Earth. It's very far away, so it's already doing it all the time.
It's just now harvesting that data.
Exactly. It's about collecting it. So this is the NIAC proposal and project to flesh out the details, to go from, wow, that's a cool idea, to, wait, talk to me about mission design. What do these spacecraft have to look like? What are the challenges they're going to have to face, which are substantial? What are the timelines? How quickly do they reach their destination? How do they map this? The light coming from this grazing the surface of the sun is contaminated by light from the sun itself. How do you deal with that? How do you point this thing? Because If I target a planet with super, super high resolution, it's like zooming in way and I see like a pimple on your face, but then that planet moves. And so I want to keep track so I can get a good image. But then how do I keep track of that as I'm moving at this extreme distance from the sun? So like all those questions that you might ask about going from that's a cool idea to how do we actually do this? That is the point of NIAC, is to start answering those questions.
Intense theoretical mathematics.
Exactly. Modeling, simulation, looking for weak spots, looking for breakpoints, looking for reasons why this idea will not pan out.
Oh, that's really exciting. Oh, wow. If that could pan out, I mean,
I would love it. I love it. It would be by far the most powerful telescope we could ever have access to.
Now, theoretically, this is still 20 years down the line.
Oh, right now, it's infinity years down the line because no NASA office has picked up this project to start to develop this into an actual mission. But we understand that at NIAC. We understand that some of the ideas we generate aren't going to happen in our lifetimes. And that's okay. We're making investments into the future where we all grew up watching sci-fi shows. We're all a bunch of nerds and we want to make that happen. And we know that the journey to make that happen starts right now. This is when we start generating the ideas. This is when we start fleshing things out. This is when we start addressing challenges. And the payoff isn't right now. The payoff is for the next generation, the generation after that. That in my lifetime, I don't think this will have like Martian habitats made out of a fungus or a telescope that sits at the focal point of the sun's gravitational lens. But maybe my children will. And that's a really cool thought to have, that I'm investing in their future and I'm making a sci-fi dream come true for them.
Wow. Now, would this telescope exist in an orbit? Or would it just be stationary? Like, how do you create a telescope that's so close to the sun, but not in the sun's orbit?
Oh, this is actually one of the major technical challenges that a telescope placed here would have to face. It is so far from the sun that it can't keep orbit. It can't keep its station. Because we have to spend so much energy, so much propellant, just getting it out there in a reasonable amount of time. And we're talking 1 to 2 decades of flight time to get out to that distance. Wow. By the time it gets there, there's no gas left. There's no propellant left. So you have to plan this all in advance. And you have to line everything up so that it passes through the focal point, takes all the data, and then just moves on. And then it's done. You only get one shot.
What?
It's one of the major challenges with these distances.
Wow.
And so the main idea behind the proposal is to not just send one spacecraft, but a fleet of many smaller spacecraft on like one after another, so that they follow each other like a train. And each of them are very simple, very lightweight, very small craft that can get there as quickly as possible. And then one takes some data, like takes a picture and it's a little fuzzy, and it passes its data to the next one. And then that one reaches the focal point, takes its picture, adds that data, then the next and the next and the next. And it builds up a picture after successive passes of these instruments, of these satellites, and then they're done. You can't repoint it. You can't train it on another target.
Wow.
And so the hope is that you can make this cheap enough to make it feasible, that you can send, say, 100 spacecraft in a row.
And they're all collecting their own data points, and then relative to each other, you're able to then pick up those biosignatures. You say, oh, this was this color on this pass, but now it's changed slightly on this pass.
Yeah, that's one potential way to do it is you scan across the face of your target. So one spacecraft enters the focal point and looks, okay, gets that pixel or like that region of the planet. And then another spacecraft gets this image, and then this image, and then this image. And then you build up a mosaic of your target exoplanet.
Oh, wow. That's so exciting.
It's cool. It's cool. And I hope we get to do it someday. And the NIAC program, it's a small fraction of NASA's budget, which is itself a very small fraction of the federal budget. There are a lot of discussions right now about funding for science and what is efficient, what is not, what is appropriate, what is not appropriate. I will say, I know some people may say it's a waste of money. Like, why aren't we trying to solve problems right now? And I get it, and that's a worth. You can have that point. Like, that's a worthwhile argument to have. I will say that it's our job in the NIAC team to prepare ourselves for the future. That when we say we want to go to Mars, when we say we want to colonize the solar system and build settlements across the solar system, when we say we want to understand the deepest mysteries of the universe, the nature of the Big Bang, there's only one way to do it. And the only way to do that is by advancing our technology.
How does a program like NIAC deal with this concept of like Moore's law, of just like the perpetual advancement, like this exponential growth in technology? And when it comes to planning for a 10-year space mission, by the time that this satellite reaches that focal point to collect data, we'll have technology that could do it in half the time. Or in 10 years more, we'll have it in half the time of that. So when dealing with future problems with current technology, is there a discussion of, hey, theoretically, this could work, but let's wait 10 years until it becomes cheaper or technology becomes more readily available to do the mission in theory that we want?
Absolutely. And that's always a consideration, not just for NIAC, for these like really far out ideas that are probably wrong, but we need to look into them to make sure if they're right or wrong. But this is a challenge that NASA faces every single day, because it takes years to develop a spacecraft. It takes years to validate and test that spacecraft. I got to visit NASA Goddard Space Flight Center. And there they test spacecraft, because a spacecraft is a very, very fragile thing that has to do very, very difficult tasks. It has to survive a rocket launch, which is multiple Gs and intense vibrations. Then it gets into space, and then all of a sudden it's 0 Gs, it's microgravity. And it goes from hundreds of degrees inside the fairing as it's punching through the atmosphere, and then it's in space and it's essentially 0 degrees, unless it's getting blasted by the sun, in which case it's back to up to a few hundred degrees. And then, if it goes in a shadow, then now you're back to like 0 degrees. It's like space is a nasty environment. So it takes years to prove that or demonstrate that a spacecraft is ready for launch. And the technology that goes into a spacecraft, it can't just be today's technology. Like, you can't just grab a processor or computer circuitry or camera gear off the shelf right now, because you don't know if that's going to work. It might be too fragile. It might not handle the temperature extremes. When they put it in NASA Goddard, they have this facility whose entire job is to shake spacecraft. They just put it in, and it's got a big platform, and it just
Really?
To simulate a rocket launch and to see if any bits fall off or things break or things or integrity is compromised somewhere. You have to test this because we don't want it breaking up when it's on its way to space. Because then
successful launch, but that wire got disconnected.
Exactly,
I mean,
exactly. Like this, we have to be extremely careful with every one of these precision instruments that we're trying to put into space. And so that's why it takes years to develop it. And you can't just take off the shelf parts. You have to go to contractors and suppliers. You have to say, hey, I know the stuff you sell at Best Buy is good to within a certain tolerance, but I need a tolerance 10 times better than that, because I can't afford for it to fail, because I only get one shot. So I need you to make a custom version of this. And then, it takes a few years to develop the custom version. And so by the time you're even sticking it in the spacecraft and assembling it, it's already years out of date, because this is such a long, arduous, difficult process. And that's just the reality. That's just the way. That's what we have to deal with, that the technology in space is always, in terms of functionality, years behind what we have here on the surface of the Earth. But that's the best we got.
Yeah, and then I guess the other difficulty, like even speaking with Dr. Kipping about the idea of exoplanet exploration, is that, okay, we do all this, we get the technology, we have all the funding, we send these satellites out, we get a picture of this exoplanet, and it's just some, the gases and
we miss.
Yeah.
Because we have promising targets, planets that sit in the habitable zone of their stars, planets that we think might be promising homes for life, but we don't know until we actually take a closer look. There's just no way to know until we get more data. And we are developing the techniques right now in the technologies to get that better data, to refine that question.
And then is there the question, like, how is the question of the speed of light and what you actually see on those planets being what is currently happening, right?
Yeah, that's always the thing. That's always a problem that we navigate in astronomy is our images of the distant universe aren't as they are right now. They are as they were when the light was first emitted, which might have been years ago. It might have been tens of thousands of years ago. For distant galaxies, it was millions or billions of years ago.
Like, could you paint the theoretical? I've heard the version of this. Like, if one of those exoplanets was looking at us and they used the same exact imaging, what would they see on Earth?
Okay, so let's say there's an alien civilization and they live 100 light years away. They're on some star, they're 100 light years away, and they've invented their version of the solar gravitational telescope so that they can paint a picture of Earth. And so they turn it on, they do it, and they point it at this promising star 100 light years away that they think there's a planet in its habitable zone, and it looks pretty promising, but they're going to get a detailed portrait of that world, and that world is Earth. And they take that portrait, their portrait is as the Earth was in 1925.
And they're like, these guys don't know anything. They don't barely have airplanes.
Yeah, exactly. Exactly. We don't even have like wide scale radio communications. We got nothing. But they would see us.
Yeah.
They would see the light from our cities back then. They would know, they may not know that intelligent life exists on our planet in 1925, but they would certainly know that there is life. They would see the forests. They would see the algae blooms over the ocean. They would see the coral reefs. If they could achieve that kind of resolution, they could see the grasslands, the rivers, the oceans. They could see the evidence for life in the portrait of our planet.
Wow. Yeah, that's like the most interesting thing when it comes to like trying to really pin down far off civilizations, that you're dealing with so many layers of complexity where it comes to, timing, the ability to actually absorb light from the time that there is, like habitation, could there be some type of alien life, even, some type of micro, some
microbes, just
whatever,
eating dirt.
But does it exist at the exact same time that we even have the imaging?
We are just now beginning to develop the technology to hear radio signals from intelligent civilizations, to study distant planet atmospheres, to look for signs of life. We may have missed a lot. The universe is 13.8 billion years old. A lot has happened in those 13.8 billion years. We're only just now catching up.
Yeah. Oh, wow. Okay. I love this. This is so exciting. What's up, guys? We're going to take a break really quick because we have a new sponsor of the show that I'm so excited about that I need to tell you. So listen up. Our food is important. What you eat is who you are. It's how you think, how you feel, how you work out. It basically encompasses everything. But unfortunately, our food doesn't have the nutrients we need to be our best. And that's where Symbiotica comes in. Symbiotica is the greatest supplement brand in the world. And here's why. They got all these different supplements. I actually take these every single day. Specifically, the magnesium L-threonate. I take this before I go to sleep, and it helps me sleep better. Magnesium is amazing for helping me go to sleep. Look it up. There's studies everywhere. And this is great because it tastes amazing. It's not some pill. This is the L-threonate. It's sublingual. It actually gets in your blood system faster and will make you sleep better, perform better the next day. And when you sleep better, your hormones reset better. You get stronger. You work out better. All that. Vitamin C, same thing. You need that. It should be in your food, but it's not. And that's where Symbiotica can be the cure. And then, of course, you got liquid colostrum. You probably had colostrum right when you were very first born. If you were breastfed, your mom made colostrum. It is nature's first superfood. It is super dense in nutrients, and right here it is in this package. It'll make you feel amazing. So if you want to perform better at the gym, if you want to perform better at work, if you want to think faster, if you want to be more social, even talking to women, oh, I don't know what to say, I jam up, I get nervous. It's possible some of that anxiety is because you are nutrient deficient. You feel bad. You don't have the adequate stuff in your body to make you be at your best. So if you are interested in being the best you that you can be, go to symbiotica.com/camp for 20% off your order plus free shipping. That is symbiotica.com/camp for 20% off your order and free shipping. This is all stuff I actually use. I'm weirdly obsessed with my health and nourishing my body, and this is the stuff that I take, which is why I'm so excited to tell you guys about it. So check it out, and let's get back to the show.
Or you wanted to talk about parallel universes.
Yes.
And then we got totally sidetracked.
No, this is, but
NIAC.
I think this is a great segue because looking at the NIAC stuff, part of me, maybe in like my sci-fi brain, is very seduced by the idea of like when it comes to space travel, it's just everything's so far and the limitations of the speed of light and mass
so annoying,
slowing everything down and the laws of physics and the da-da-da-da-da-da.
It's not fun.
It's like, it's just so bound by reality.
Yeah.
And part of my hope is that in the way that we understand space and time, and when I say we, I mean people like you and
the collective we, humanity. The things we derive and understand in science belong to all of humanity.
My IQ is being lifted up by this collective we. I'm very grateful for this royal we. But this idea of our understanding of space time, that could we mitigate time by, sort of pulling some clever physical loopholes with space.
Like, are there any cheat codes?
Are there cheat codes to, accessing a distant planet, maybe using, something that exists in the metaphysical realm or some type of parallel universal realms, things like that. So can you take me into those waters? Obviously, I mentioned the article that you had written about this idea of parallel universes.
Yeah, let's go there. Let's do that. Let's start off by saying, I hope we're wrong. I hope 100 years from now, physicists look back at our understanding of the universe, the understanding of the universe that I have and my colleagues have. And I hope they laugh. I hope they snicker. I hope they say, man, how ignorant were they? How short-sighted. Oh my gosh, they didn't figure out this. And then they couldn't understand it. It was right in front of them the whole time. Yeah. The evidence was all right there. But I hope they say that because that means there's a lot more to learn. My worst nightmare, second worst nightmare after being eaten alive by ravenous monkeys is that we don't ever progress or our progress slows down in physics and our understanding. And that 100 years from now, they're like, yep, still don't understand quantum gravity. I'm like, oh man, that'd be a bummer.
Yeah, it would be.
So I hope we're wrong. But this is all we got. Is our current understanding of physics. And with our current understanding of physics, we can say some things are definitely off the table and some things are highly unlikely, but there might be some wiggle room there. And then there are some things that we can say are totally good. We all clear to do it. When it comes to parallel universes, there are two ways to approach a parallel universe. There are two places in physics, in physical theories, where the concept of parallel universes naturally emerges. One of those is through our conceptions of the Big Bang and through our attempts to understand the incredibly early universe. There are some theories called the multiverse, or fit under the broad category, this umbrella term of the multiverse, where our Big Bang was not alone. That the universe, the entirety of physical existence is much larger than what we would normally think of, that there's not one singular universe with one Big Bang, one history, one development of stars and galaxies and people and whatnot, that there are multiple branches of that Big Bang, that Big Bangs happen a lot, that they happen frequently, that they can chain together, that in the far distant future of our universe, another Big Bang will spark, that there's some location out there beyond the borders of what we can observe in our universe where Big Bangs are currently happening, where there are other universes. The imagery I like to have of the multiverse is a foam of bubbles where we live in one tiny little bubble, but next door to us, relatively speaking, it's incredibly far away, but next door to us is another little bubble. And they got their little Big Bang, they got their stars and galaxies, maybe they have some weird stuff, maybe they have different laws of physics manifesting in their little bubble. And then there's a little bubble over there and a little bubble over there, a little bubble over there. This is deeply theoretical. This is at and beyond our current understanding of physics. There are some intriguing hints, some intriguing ideas of how you might be able to generate a multiverse this way. But there are some things we can say about this multiverse and accessing those other universes. One is those universes are here right now. They exist, not in another dimension, not in some parallel reality, but over there. Like if you point in one direction, and you go and go and go and go, and you go outside the bounds of our observable universe, 45 billion light years away, and then you keep going, and then there's vast expanses of nothing, you will eventually intersect one of those other universes, that they exist in space simultaneous to our universe. But they are receding away from us. Their bubble, this foam that we live in the multiverse, is getting bigger with time. So the bubble of that multiverse, of that other universe, I think you can pull up some images. If you just do a generic Google search for multiverse, you can get some like pretty cool graphics and images that show this very well. Because these bubbles are receding away from each other, they're actually receding away from each other faster than the speed of light, which means you can't ever get in a rocket ship and go there. You can point to it. You can say, oh, yeah, it's over there. Oh, yeah, check that out. Look at that. We got bubbles. We got universes. So there's us. There's our cosmos with our... I don't like the multicolored one. That's lame. But the first one was better, actually, because that's the cosmic web. That's the large-scale structure of our universe. That's what our universe looks like at the very biggest scales. And so that's us. And then, a certain distance away is another universe with its own cosmic web. And then between us is essentially nothing. But these bubbles are receding away from each other faster than light.
I don't like that.
I'm sorry.
Faster than light.
Okay, so we got to address the faster than light elephant in the room, because this comes up all the time in cosmology. And it also comes up like, YouTube and social media is a weird thing. I'll make a podcast episode or a YouTube episode, and I'll talk about how like even distant galaxies can recede faster than light. And then it's guaranteed to get a flood of comments like, you don't know what you're talking about. I'm like, I'm pretty sure I passed freshman physics, and then I passed sophomore physics, and then junior, and then senior physics, and then graduate school. And of course I earned a PhD, man, and I'm going to wave this thing in front of you. I have a picture of my diploma on my phone just in case, I earned it, man. I'm pretty sure I know what I'm talking about. I'm like, literally, I don't know. That's just an annoying thing. Sorry, I'm not here. This is not a therapy session. I'll save it for my next therapy appointment. Yes. The special theory of relativity says that things cannot go faster than the speed of light. But we have to remember that the special theory of relativity is a local theory of physics. It's a theory of local physics. It tells you what happens in your vicinity. You will never, ever, ever, ever see a rocket ship blast by you faster than the speed of light.
Okay, that's good.
You personally will never travel faster than the speed of light. It's all good. But there is a broader theory, a more general theory of relativity. We call it the general theory of relativity.
I've heard of that.
That tells us about the behavior of objects that are very, very far away. And when objects are very far away, like billions of light years away, the conception of speed that we have in special relativity doesn't necessarily apply. A distant galaxy can have whatever speed it wants because it's too far away from you. Up close, if you were to be close to that galaxy, you'll never see that galaxy whizzing by you faster than the speed of light. But when it's on the other side of the universe, it can have whatever speed it wants. And in fact, because we live in an expanding universe, the distances between galaxies is growing with time. The galaxies themselves aren't moving. There are no rockets attached to the galaxies. There are no propellers that wouldn't work in space, but there are no propellers. There's no movement or serious large-scale movement of galaxies. There's some small stuff that we map out, but it's nothing. It's nothing. If we're right here, and if we could visualize the fabric of space in our universe, we can lay down a grid. This grid is getting bigger, which means I can draw an X right here under my feet, under the Milky Way galaxy. And I wait a while, the universe expands, and I check, and the X is right here. The Milky Way galaxy hasn't moved. Not substantially. It's moving a little, but we don't need to worry about that. The X is right there. Everyone in the Milky Way galaxy agrees, and all of our neighbors agree. We check, hey, Andromeda, have we moved? And Andromeda's like, no, you're good. You're right there. I see the X is right there under your feet. You haven't moved. A distant galaxy, 20 billion light years away. They drew an X on their fabric. They drew an X under their feet. And they ask all their friends, hey, have I moved? Is it me? Am I getting fat, or is the universe like, is this me? And everyone says, no, you haven't moved. You're good. You're standing perfectly still. But the space between us is expanding. So even though we haven't moved and the distant galaxy hasn't moved, we're still further apart because the space between us itself is growing larger. So no violation of relativity, no violation of the speed of light rule, because nobody is moving in their local frame of reference, but the frame of reference itself is moving, is expanding.
This theory is nice also because it answers that question of if the universe is expanding infinitely, if there's an inside, what is the outside? What is it expanding into?
What is it expanding? It's a lovely question I get all the time. More lovely than the you don't understand physics accusations, which are always amusing. But they're like, what is it? Because it's hard to visualize. Forget the multiverse. Say we're just one bubble. This gives you an inaccurate representation of what the universe actually is. And it's very, very hard, in fact, impossible to visualize, to hold in your head what the universe actually looks like and what it means to live in an expanding universe. To live in an expanding universe, which we do, means that the distance between galaxies on average grows with time. That's it. That if you take a ruler, if you press pause, take a ruler, measure the distance between two galaxies, press play, wait a while, press pause, measure again, you're going to get a bigger number. That's what it means. On average, of course, there's extra little motion on top of that, but on average, this is true. That said, the universe has no center, and it has no edge. It's not expanding from into anything. I'm sorry, it's not expanding from anything, and it's not expanding into anything. The universe didn't come from anywhere, and it's not going anywhere. That's because the universe is literally all there is. If it was expanding into something, that means there is a space. There is like a void. It could even be nothing. But that's a thing. And last time I checked, the definition of the universe is all the things. So we'd have to count that in the definition of the universe, which means the outside of the universe is also part of the universe. The universe is literally all there is. It's not that there's nothing outside the universe. It's that there's no such thing as outside the universe. So it makes no sense to talk about the universe expanding into something because something has to be a part of the universe. But the universe is all the things. It's all the somethings. So how can the universe be expanding and yet not have a central point from which it emerged and not have anything to expand into? That's math. This is one of the beautiful and terrible things about being a cosmologist, which is we have developed tools, mathematical tools, to understand the universe and to grapple with it. We can model the expansion. We can make predictions. We can understand what's happening in the evolution of the cosmos. I also can't visualize it. I can't put it in my head. I cannot think of a three-dimensional universe that is expanding, but there's no such thing for it to expand into. I can't visualize that. I can't hold that in my head. But we invent tools to do things that we normally can't do. I can't also like pound a nail into a board with my fist. That's why we invented a hammer. We invented a tool to do something that we normally can't do. We invented mathematical tools to take our minds places that they normally couldn't go. And that is beautiful and powerful and poignant. It is also really annoying because I daily grapple with questions that I can't fit in my head.
Wow. Yeah, that is a difficult thing to conceptualize. That we just trust the mathematical tools.
We don't trust it. And there's no such thing as trust in science. But we know that the tools work and we demonstrate them based on the evidence. And so we go with that for now. But no trust. Oh, no.
Acceptance, maybe? Reliance?
Resignation.
Yeah. Defeat.
Yeah, just okay, it's the best we got. No, if it demonstrates itself to work, then we keep using it.
Okay. So now into the theoretical multiverse idea.
Yes, back to the multiverse. So in the multiverse, our universe could be expanding into a vacuum beyond which are even more galaxies or even more universes. And it's okay for those universes to be receding away from us faster than light. That just means that you can never reach it. That if you set off in a rocket ship, you'll never, ever be able to catch up to it. The same thing is happening in our universe. There are distant galaxies that are receding away from us faster than light, which means the light that we see right now was emitted billions of years ago and is just now reaching us. And if you were to set off in a rocket ship towards that galaxy, you would never reach it. Eventually, it would fade from view and disappear. This, with the multiverse and these other multiverse universes, the same thing applies. They're receding away from us faster than the speed of light. You can never reach them. So that sucks. So you can't access the multiverse by getting in a rocket ship and going really far. But there's another entry point for multiverses in our theories of physics. And that other entry point is through quantum mechanics. Quantum mechanics is super weird. Quantum mechanics makes no sense. Nobody understands quantum mechanics, and including physicists. And if anyone tells you they understand quantum mechanics, they're lying to you. What they mean is they understand the mathematics of quantum mechanics. Like, I understand the mathematics of quantum mechanics. I know how to operate the machinery to generate predictions, but I don't understand what's happening at a subatomic level. Nobody does. One of the most mysterious things about quantum mechanics and about the subatomic world in general is that probabilities rule the day. That if you shoot a subatomic particle like an electron through an experimental apparatus, it might go left, it might go right. You can't predict which way it goes. You can't. There is absolutely no way to predict with absolute certainty if it goes left or if it goes right. The best you can do in quantum mechanics is assign probabilities, like 50-50 shot of going left or going right. That's our foundational observational reality in quantum mechanics. We've tried and tried and tried for over 100 years. We cannot break this. The subatomic world plays by different rules, and these rules are based on probability. Now, we've wrapped these probabilities in mathematical language so that we can make predictions of what's going on, so we can validate experiments. These mathematical tools that we call quantum mechanics have proven to be enormously successful, enormously accurate, and enormously powerful. It's unlocked the subatomic world for us. So everything from modern chemistry to nuclear weapons to circuitry are all based on our understanding of quantum mechanics. So we're pretty sure we're doing something right, because every time we access the subatomic world, the rules of quantum mechanics hold. But these rules of quantum mechanics are very, very strange. They are not rules that we apply to the macroscopic world. Like the laws of physics or the theories of physics, however you want to cast it, in the subatomic world are very, very different and unfamiliar than what we use in the macroscopic world.
Schrodinger's illustration of this is done to show how absurd it is to try to apply them.
Yeah, in fact, Schrodinger's cat experiment was done to show how much he hated. He actually reviled the development of quantum mechanics. He was one of the original leaders in the quantum movement and the quantum revolution, and then he ended up hating the direction it was going with this reliance on probabilities, and he ended up being disgusted by it and came up with this cat in the box experiment, thought experiment, to demonstrate, like, you have no idea. We have no idea what's happening in the subatomic world. And then he would leave quantum mechanics and spend the rest of his life working on other topics. And it is true. He has a valid point. We do not fully understand what's happening. One of the ways to address the probabilities that appear in quantum mechanics is to say that maybe it's not probabilistic at all. Maybe when we do an experiment where we like shoot an electron down and it has a choice of going left or going right, maybe it does both. Maybe it goes left and right, but we only get to observe one of those possibilities. And that there is another set of observers, another us, that observes the other one. This gets rid of the probabilities because all possible interactions and results of the experiment come to fruition. So you don't need to make arbitrary choices about, cutting this off or cutting that off or truncating. It just all happens, but different observers, different universes encounter different results. So at the moment that the experiment happens, the electron in our universe goes left, and we write that down. Okay, they had a 50-50 shot going in the experiment, and it went left. And then there's another set of observers, a copy of us, that say, oh yes, 50-50 shot, and the electron went right. So both realities happen simultaneously. This interpretation of quantum mechanics is called the many worlds interpretation. It's a minority view within quantum circles, although most physicists don't think about the philosophy of quantum mechanics. They don't think about the foundation of quantum mechanics very much. It has some challenges. We don't need to go into some issues with its interpretation, but let's go with it. Let's just say, okay, let's make this happen. The many worlds interpretation of quantum mechanics, let's say it's legit. That means every single quantum interaction that's happening, of which there are many, is spawning divisions of the universe, multiple copies of the universe. A particle went left in one universe and it goes right in another. And there are observers, there are you and me's, there are stars, galaxies, planets, the whole universe where everyone agrees the particle went left. And then there's a whole other universe where everyone agrees the particle went right. That means when you get in a car and drive down the road, the quantum mechanical interactions happening in the engine of that car, you're spawning like trillions of universes per second. It's a large number, but okay. So there are all these parallel universes, these many worlds that are happening simultaneously to our own. So the question is, how do you access them? Because they're over there. They're a whole separate reality, a whole different branch on this quantum tree. How do you go there? How can you move over there? And the answer, potential answer, again, this is all speculative, theoretical, but really fun to talk about, is wormholes. A wormhole is a shortcut through space and time. The idea is, and you can pull up like a cool image, it's like a tunnel, it's a throat, it's a okay, man, I really want to go to that distant star, but yeah, that's a great visual. I want to go to that distant star, but man, laws of physics are a major bummer. Maybe I could have a shortcut. Maybe I could bend space and time in just the right way that I could just take a shortcut. Okay, wormholes probably don't exist, but let's pretend they do, because we want to follow this line of thought. We want to access our parallel universes. Wormholes aren't just shortcuts in space. They are also time machines. If you have a wormhole, you have a time machine. You already do. It's already done for you. You've built a time machine. You can arrange a wormhole so that you walk in one end. Let's say you walk in the top, and then you walk down. We'll build a sidewalk for you, or like a handrail that you can pull yourself along. You go through the other end. You end up in your own past. That's what a time machine is. And it's pretty straightforward to arrange with a wormhole. They're not just shortcuts in space. They can also be shortcuts in time. You can travel forward, never going faster than the speed of light, never doing anything weird, no dilithium crystals or anything like that, and you just end up in your own past. The possibility of time travel through a physical mechanism like this, like wormholes, opens up a lot of questions, a lot of angst, a lot of paradoxes. Like the famous grandfather paradox. Like, what if you travel back in time and kill your grandfather? Your grandfather never lived, so you were never born, but then how did you exist to go back in time?
Mm-hmm.
You can also go back in time and destroy your own time machine. You can close the wormhole. You can flip the switch off. You can plant a bomb so it blows up when you go back in time. But if you went back into your own past and turned off the time machine, then, or destroyed your time machine, then how were you able to travel into your own past to turn off the time machine or blow up your time machine? It's a paradox.
Right.
There are all these paradoxes. The universe seems, as far as we can tell, to follow a regular ordering of past to present to future. That causes always lead to effects. That you can't have it the other way around. But as soon as you build a time machine, you can have causes coming after their effects. You can have uncaused effects. You can have things that just happen for no apparent reason. You can have a memory of the past and yet change that past. So how are those two things compatible? Wonderful questions. Glad you asked. One line of thinking is that the past is the past. This is called the chronology protection conjecture, which is a very difficult set of 3 words to say without garbling. It's a great tongue twister.
Chronology projection protector.
Chronology protection conjecture.
Dang.
So close.
I know.
Now say it 10 times fast. Yeah.
Chronology protection conjecture.
Yeah, because we're protecting the chronology.
Yes.
And it's just a guess, so it's a conjecture.
Yes.
So we could have said that better, but this was Stephen Hawking. It's all his fault for using the fancy words. So the chronology protection conjecture says that the past is just the past. It's locked. That yes, you can travel back in time if you want, but you can't alter the past. Because it's already there. It's already happened. It's already led to the present set of causes. The present set of effects. It's already here. The universe has already happened. World War II already happened. You can't go back and kill Hitler because he already lived and World War II already happened. You can't change it. There it is. Yeah. Okay. Chronology, protection, the CPC. We'll just call it CPC from now on. We're gonna go easy on ourselves because it's a mouthful. You can't change the past. But then if wormholes are real, they can be time machines and you can go back and change the past. So which is it? Is there a way to have both? Is there a way to protect the past? The past is always the past, and have time travel. A potential answer is the many worlds interpretation of quantum mechanics, where when you go into the past, this is assuming wormholes exist, assuming time travel is possible, assuming the many worlds interpretation of quantum mechanics is valid. When you step into your time machine, you travel down that wormhole, you pull yourself along the handrail, you end up in the past. It's not your own past. You end up in a different past. You end up in a different branch of the many worlds tree, a different branch of the quantum tree. You go back. Let's say you go back in time with the mission to kill Hitler. You want to avoid the Holocaust. World War II, and you're going to do it. You plot it out, you built your wormhole, and you show up, you're like, Hitler, bam, you got him. Now you are not in your past. You're in a different past. When you come back to the present, Hitler still was alive. World War II happened. The atrocity of the Holocaust still happened. That's because that's your past. You changed someone else's past. You changed a different branch of the tree. In that branch of a tree, their past, everybody knows that a time-traveling assassin from the future, from an alternate dimension, killed this like random failed painter politician
for no reason.
In Germany for no reason. Nobody understands why. That was always their past. And it was always their past. They will always remember it. Nothing changed. You just scooted over to a different branch of the tree.
Now, does that create a new quantum tree?
In this idea, the real answer is no one knows because it's all super hypothetical and speculative. In this picture, I think the large thinking is more along the lines of that path already existed. It was already some combination of quantum interactions where that possibility that there is already in parallel to us a universe where Hitler was killed early on, and that Hitler was always killed by a time-traveling assassin from a parallel dimension. And it was always there. The quantum probabilities already added up to give rise to that universe, and so you're simply playing your part.
But then, if the past is locked, and under this idea that quantum past was already always that way, that a time traveler came back and killed Hitler, that would mean that the future in some capacity is also locked. And then we are in this sort of determinist reality where all past and future is locked in all these quantum universes.
Yeah, even though you have this, that's a wonderful insight, and I'm glad you brought it up, that even though we have this infinitely branching quantum tree that contains every single quantum possibility, that all the possibilities already exist. All the potential universes have already been manifested and exist in some sense parallel to our own. And that when you're doing this, you were always going to do it. You were always going to travel back in time. You were always going to kill that Hitler, not your own, but someone else's Hitler. But that branch already existed. It was already there, which means all of our future choices are already predetermined because they already exist on different branches of the quantum tree. This is actually one of the major objections to the many worlds interpretation of quantum mechanics, which is like, if all the potential outcomes already exist, how does the universe know to give me a 50-50 shot of this electron going left or right? You still have to fold in probabilities somehow. And it's not exactly clear how. Also, this opens up this broader philosophical question and somewhat scientific question of, well, if the past is locked, is our future also locked? Is our sense of the progression of time, is our sense of the progression of the choices we make, of the randomness of quantum particles, of whether to get oat milk or almond milk in my latte, are these choices are they already made? And is all of this our progression of time from past to present to future? Then the choices we make, is it all an illusion? Is it all just a product of our conscious experience of the universe? Does the universe already exist? We know the universe exists in 3 spatial dimensions, like left and right, up, down, forward, backward, are all right there. Like the galaxy over there is right there. The tree is right there. Is my future already right there? I just have yet to experience it or become aware of it. That's above my pay grade.
Right.
I'm just a cosmologist. I'm just like a poor country cosmologist. Man,
just an Ohio boy figuring it out.
Yeah.
You know? But the notions of free will are not like the question, this free will question is not, obviously strict to cosmology.
Absolutely
people like
not.
Robert Sapolsky at Stanford and Sam Harris and many other, modern intellectuals that are sort of kind of pushing against this notion of free will.
Yeah, I mean, it's and there's a long intellectual tradition of pushing against the idea of free will or trying to understand what is the nature of free will. And these questions about, is the universe purely deterministic? Is it not? Is it deterministic in ways that we don't fully understand? Is it not deterministic at all? This gets at a central question in physics, which is, for hundreds of years, we've developed theories that are deterministic. All of our laws of physics are deterministic. That if you understand the present state of a system, you can predict how that system will behave. This is how we've achieved so much remarkable progress in physics. And this applies to subatomic systems. You have to modify some things. You have to introduce probabilities instead of strict, progression. But, probabilities are better than nothing. We could apply it throughout the universe. We can predict what the universe will be like 1 million years from now, based on our knowledge of physics. And our knowledge of physics is incomplete, but as we continue to develop, this overall program of determinism seems to be working out well. But then we encounter the human brain.
But still, that exists on a spectrum of probabilities, right?
Perhaps.
Right. Yeah, I guess this is a greater fundamental question of free will, right?
Exactly. That is the question. If I choose, what's for dinner tonight? Am I having, what do you have? What are your choices for dinner tonight?
Tonight, my wife is making teriyaki.
Teriyaki what?
Like steak stir fry.
Steak stir fry, or let's go with chicken stir fry. You have two choices.
Mm-hmm.
There is no law of physics that can predict with any amount of probability whether you're going to choose steak or chicken.
But couldn't you say that the probabilistic nature of human choice is just from an incomplete data set, right? Like, I've heard this theory that you flip a coin, it's 50-50. But if you understood the exact wind conditions and the atmospheric conditions and also the weight of the coin and also the force that you pushed on it, hypothetically, with complete data, you could know with 100% certainty if it would be heads or tails. And so if we kind of shrink that down and also multiply it within our brain, is it possible you could understand the data set of the mind as a computer to have 100% certainty of what the outcome would be, whether it's steak or chicken?
This idea has a name. Can you pull up Laplace's demon? This is a there's Laplace. Look at that guy, Pierre-Simon Laplace. He was a French physicist and all-around super smart guy. Did a lot of work in mechanics, and he came up with this idea that he called a demon, which was, imagine you have an entity, not us, because we're kind of dumb, but some entity, a godlike being, that had complete knowledge of the universe, exactly what you're describing, down to the molecular level, the subatomic level. This demon could predict every decision you make, every outcome of every coin flip. Yes, we have to fold in quantum mechanics. Laplace, great guy, didn't know about quantum mechanics. We hadn't invented it yet. So you do have to replace strict 100% factual knowledge or certain knowledge with probabilities. But that's okay. But you can still make predictions. You can say, well, there's a 82.3% chance that you will pick steak tonight. That's once you fold in quantum mechanics. So this is a very old idea. And the idea is that it might be possible to uncover with sufficient knowledge the real deterministic universe and be able to predict, even with some massaged quantum probabilities, but be able to predict what you can do in up to and including every single conscious choice you make.
Mm-hmm.
That's one possibility, and it's worth debating and worth arguing about. There are also other possibilities. There are purely non-physical possibilities, that there is something special and non-physical happening in our minds. There is something divine. There is something supernatural. That is a position many, many billions of people take. And so that is a very valid position. There's also something in the middle where if you ask, and I'm not a strict philosopher, all scientists are philosophers, but it's a very specialized kind of philosophy. But my impression is that the vast majority of philosophers who think about this believe that it's somewhere in the middle, that perhaps our understanding of determinism might be a little bit flawed. For example, and they point out, if you're choosing steak versus chicken, if you choose steak, there's nothing that violates the law of physics, any known law of physics, any known law of determinism for you choosing steak. There's also nothing that violates the law of physics if you choose chicken. So the outcomes of the choices are all totally valid. Where the problem seems to appear is the choice itself. So maybe this language that we have of determinism that we've used successfully and deployed successfully for hundreds of years in our understanding of the physical universe, maybe it has a shortcoming when it comes to conscious choices. We don't know what that shortcoming is. That shortcoming might be revealed by a more updated law of physics, a better understanding, a more nuanced view of determinism. That's something for our descendants to figure out. It's not something we have access to right now. But that is a third way. And that is the way that helps me sleep at night. Because I personally, just speaking as like a human being, I don't like the idea of living in a deterministic universe. I like the idea of free will. I like the idea of being in command of my own choices and my choices having an influence on the world. That's a very powerful and activating worldview for me to have. But that's just taste. That's just a matter of taste. What the universe actually does not care about our personal taste or distaste of it. So I acknowledge that. But as long as this debate is here and we have these options in front of us and it's not exactly clear which one is right and which one is wrong, that's the one I like to pick so that I can sleep better at night.
Yeah, I think that's a reasonable position to accept that this may be the case, that we have proper agency and autonomy to do what we wish. But if you were to map someone's brain from the moment that they're conceived, and even in utero, the kind of inputs that their brain has, and you're able to know every single atom, even just on like a broad scope with this example. Yeah. If I was Hindu and you asked me, are you going to choose steak or chicken? Based off of my life experience growing up as a Hindu, there's a very high likelihood that I would probably choose chicken.
Or neither.
Perhaps, or neither, right? If I was a vegetarian Jain or something, I would pick neither. And so it's one of those things where you can look at cultural influence and family influence that then changes the atomization of your brain. And this is looking at a strictly on a material level, which obviously within your realm of work, you might not necessarily consider as heavily this perhaps spiritual level that exists immaterially. Right. Yep. Which is at this point unquantifiable. And if it is quantifiable, then maybe it no longer is spiritual, and that
then it's just, and we just bring it over here into physics.
Exactly.
But we can't immediately discount it because there are many aspects of the universe that we do not understand. There are many aspects of the universe that do not fit into physics, that physics has no accounting of. And that's okay. It's like I always tell my fellow physicists and other scientists, like, it's okay for us to not have all the answers. I tell the public, do not look to science for all the answers. We are the last people you want to have answering questions. Because
last time you were here, you said basically this exact thing, that you can look and exist in a very physical material world, but then also have a faith that exists outside of it.
It's perfectly possible. It's perfectly compatible.
And in this exact example, you're like, I have a faith that I exist in free will.
Exactly.
Despite not necessarily having concrete...
No evidence one way or the other. Right. And obviously there are things like, there are cultural and material influences. Like, we are not purely random or agents of our own destiny. There is some level of determinism that influences our future choices. It influences the things that we can imagine and the things that we are capable of doing in our own life and even as a humanity, as a species. And then there's a lot we don't understand, and that's okay.
What's up, guys? We're going to take a break really quick because I got to tell you about a dirty little secret, okay? The insurance industry doesn't want you to know this. Well, basically what the insurance companies do is that they profit by holding on to your money as long as possible. You pay them every month, and then eventually when an accident happens, they try to deny or delay your claim so that they can keep their profits going. I mean, it goes even worse. When in court, the insurance companies want jurors to think that the at-fault driver a mom that rear ends someone, she's a single mom, and they think that she is going to be paying the verdict amount. Meanwhile, it's really the insurance companies who are going to be covering the cost. And that's why I want to tell you about the good folks over at Morgan & Morgan, because they will take on the case, and they are almost always going after the big insurance companies and not the individuals at fault. Morgan & Morgan fights hard for their clients, and these corporations know that, and it pisses them off. A recent client in Pennsylvania just received $29 million. The insurer's best offer, $500,000. Yeah. There's another client in Florida that received $20 million, and the last offer from the insurance company was $0. There's a reason why Morgan & Morgan is America's largest injury law firm. So if you are ever injured or dealing with an insurance company that doesn't want to pay up their fair share, you could go check out Morgan & Morgan. That's right. Hiring the wrong law firm can be disastrous, and hiring the right law firm could, be a big, substantial increase to your settlement. And Morgan & Morgan makes it so easy to get started. Their fee is free unless they win. There's literally no risk. Unless they win your case, you're not paying a dime. And with Morgan & Morgan, it's never been easier. I'm telling you. You just go to forthepeople.com. That's right, forthepeople.com, and use the code GAGNON, GAGNON, or dial pound law. That's pound 529. That's forthepeople.com/Gagnon, or dial pound law. That's pound 529. And this is a paid advertisement. Now, ladies and gentlemen, let's get back to the show. I had mentioned before we started recording this idea of Schopenhauer's, you can do what you will, but you cannot will what you will.
Ooh.
That you can choose steak or chicken. And because you can do what you will, and what you will is to have steak, and so you're going to choose that. But can you choose what you want?
Yeah, that's a very powerful distinction.
Like that feeling of, I want chicken. And then let's say, okay, that violated my freedom of choice. The next night, I'm going to choose chicken. But are you really freely choosing chicken, or are you choosing to will your autonomy?
Right.
But you didn't actually will that will to choose one or the other. You just tried to will your choice.
Yeah, that's a very powerful question, and I have very little to contribute to in addition to it, besides my cosmological musings.
Yeah, but it is interesting that Laplace's idea, did this pick up steam in the time that he was discussing this?
He was like super hardcore atheist. He was like, oh my gosh, all of you religious nut jobs are crazy. I'm going to prove to you that he's a very interesting character. Obviously this idea survived not just in physics, because like all of physics is deterministic. This is how we make progress. And that was his major contribution, was applying this kind of philosophical principle to things like mechanics, Newtonian mechanics. He came right in the generation right after Newton. He was able to expand on Newton's work and broaden it into a wide variety of applications that continued a long tradition in physics that persists to this day. His philosophical musings, I don't know how much of an impact it had, but he's a major figure in the history of physics. Also a very swanky dresser.
Absolutely.
Of which I applaud him.
Yeah, it is nice.
Yeah.
I wish more scientists dressed like
we
this.
should bring back sashes.
Yeah.
and not just for Miss America pageants, but professional dress sashes.
I think that would look nice on you.
I appreciate it.
Cosmologist.
Yeah, all the cosmologists get to wear like blue or black or something.
Forget Miss Universe. I want Mr. Universe.
Mr. Universe contest. Look at that guy. And high neck. There's
Does this intersect at all, or this multiverse idea, does it intersect at all with like simulation theory?
Absolutely not.
In no way.
No, and it's well, I mean, I'm sure if this conversation went on long enough into the night, we could find an intersection between this. The simulation theory is its own giant can of worms, which has no clear answer. There are a lot of issues with the philosophical arguments that lead to this conclusion. It's not exactly clear that there is a conclusion to be made. And you could say, okay, like we live in one simulation, and then in the box next door to us in the real universe is another universe, a simulated universe, and they've got their own Laplaces, and they've got their own chickens and their own steaks. That's one way to say the multiverse, but that's not a physical multiverse. That's not the way we understand a multiverse through our theories of physics. That's a way to say there's a conception of a multiverse that comes from these more philosophical arguments about the fundamental nature of reality.
I did want to ask you about the New York Times article that you did.
Yeah.
This notion of being alone in the universe. At least, maybe not literally, but at least observably.
Observationally, right? As far as we can tell, we're super alone.
And you said that shouldn't be fear-inducing.
No, it's actually, this wonderful article that I was very lucky to be able to write this essay for the New York Times and get these thoughts out into the world. And you can use my email address to log in.
But why should that give us meaning?
So, observationally, the universe is large, it is old, it is cold, and it is empty. These are facts that we cannot ignore. After a century of cosmological observation, this is what we have revealed. In fact, the focus of my research is on something called cosmic voids, which are the vast empty regions in the universe that dominate its volume. Things hundreds of millions of light years across where there's nothing. There's just nothing. It's just empty space. And there is this temptation to look out on like a clear, dark night, see thousands of stars in the sky, to contemplate the enormity of the universe, which is something I have the privilege of doing every single day. That's a part of my research. And to recoil from that and to shrink into cosmic insignificance, like this pale blue dot, like we're just this little speck of dirt, a little bit of water, orbiting just another star in just another galaxy. There's nothing special here. There's nothing unique here. We are tiny. You could erase the Earth from existence, and the cosmos wouldn't even notice. It would continue expanding. Stars would still be born, and stars would still die. There is that temptation, and I reject that temptation. I refuse to say that we are cosmically insignificant, because there is something special happening here on the Earth. It's happening right now.
You mean here, or you mean somewhere else? There's like a football game.
Was I about to propose to you?
Yeah,
that seemed like a lead. That was like a very romantic lead up.
I feel like we both put our hand on a book. And we're like, we're connected.
Spark. There is something special happening on the Earth. We are the only known place in the universe that is alive. The only known place, and we've really looked. Now, there might be life somewhere else, for sure. But if it does exist, it's incredibly rare. We are the only known place in the universe where laughter exists, where art exists, where politics exists. There's nowhere else that we know of. We've looked. There's nothing out. There's literally nothing out there, which means it imbues the Earth and what we have here with our history and our ability and our curiosity. It imbues it with meaning. It doesn't make us cosmically insignificant. It makes us the most important thing to be happening in the universe. Oh, a giant star blows up over there. Okay. Happens all the time. There's nothing special about that. A galaxy forms, whatever. There's like literally billions of them, just like it. Life appears on the Earth. Intelligent life appears on the Earth. We're able to peer out into the universe and try to glean some meaning out of that. That's special.
That's a great point. I really like this. This is like, even as you're saying it, it's very compelling, because you have to wonder if, let's say there was infinite other, galaxies or infinite other star systems with other life, that would make us more insignificant. Like, oh yeah, life is not unique. It happens all over the place.
Life is boring. And I do believe, not based on any evidence, that there is life in the galaxy and other planets, and probably intelligent life, occupying our universe along with us. I do not like to think that we are alone. But even then, if it if it happens somewhere else, it's definitely rare.
Mm-hmm.
It's definitely one of the rarest things to ever happen in the universe. And let's say we make contact or receive a signal or see evidence, we see a biosignature of some intelligent civilization, and it's just us in the night. That's it. That means something special is happening here, and that the universe, the enormity of the universe, does not rob us of our significance. It amplifies it because we get to do something here that nowhere else in the universe is experiencing, and we should treasure that.
Yeah, that's wonderful. I think that's a great perspective. Yeah, I really like that a lot. And I'm curious about this idea of you said it's old, the universe, it's ancient. I was actually talking to a professor, a philosopher that studies the history of science. And a lot of these early philosophers like Plato, even all the way up to like Copernicus and Galileo, they were sort of required by the state of the time to talk about the eternality of the universe, that it was eternal. Do you think that there's something to be said for the universe existing into perpetuity in both directions, that it is eternal, that it seems like there's a constant push to put a date of when the universe starts, and it seems like it's constantly getting pushed back by billions and billions of years. And it almost seems like a futile task to say like, oh, it began here. And is there any benefit to saying that it is eternal? Is there any credence to that idea?
So our current measurements suggest that the universe is 13.77 billion years old. And we worked really hard for that second decimal point, and I'm not going to give it up. This is actually an extremely radical idea, a very, very fresh idea in the consciousness of humanity. This is an idea that's only about 100 years old, with the birth of modern cosmology and the discovery that the universe is expanding. Prior to that, in the late 1800s, early 1900s, the default assumption that the universe was just the universe. It just exists. It's just a thing that's always been a thing. Yeah, like stars might form or blow up, and you might have a planet over here for a while, and then it goes somewhere else. That stuff within the universe is temporary, but the universe itself is just the universe. But then with the cosmological revolution, our understanding of the Big Bang, we find that we live in a universe with a finite age. And this, to me, is one of the most powerful statements made by science. And I don't say that because I'm a cosmologist. I'm a cosmologist because I find that statement powerful. That's one of the reasons I chose this line of research. To say that our universe had a beginning is wild. It's bizarre. It seems almost biblical. In fact, one of the first people to state this was Georges Lemaitre, a Belgian priest. And he was initially ridiculed because this idea sounded way too Catholic. And it turned out to be kind of right. Yeah, you can pull up a picture of Georges Lemaitre. There he is. Look at it. He conceived of the idea of what we now call the Big Bang as the primeval atom that essentially exploded and unfolded into our universe. And he got this idea from he was a researcher. He was a scientist. He was, in addition to being a priest, he was a mathematician. He was brilliant, and he looked at Einstein's general theory of relativity and discovered the mathematical underpinnings of what would become the Big Bang theory. Now, like I said at the beginning, I hope we're wrong in terms of all of our laws of physics. As far as we currently understand physics, the universe is 13.77 billion years old. We also do not understand the origins of the universe. We do not understand its earliest moments. We only have a hazy understanding of what the universe was doing. Starting about a few minutes in, that's when we can start to grapple it with known physics. Earlier than that, we just don't have the tools, the technology, the mathematical language, or the philosophical underpinnings to grapple with that early epoch. So to say that the universe might be eternal or that our Big Bang came from somewhere, this is actually a very fruitful way to approach the Big Bang, where our universe as we understand it is 13.77 billion years old. But what caused the Big Bang? Does it make sense to say that the Big Bang had a cause? Was there something in existence prior to our Big Bang? These are very powerful questions, very essential questions, and questions that break our current knowledge of physics. We have no definitive answer whatsoever. We have some wonderful ideas. We have no idea if these ideas are even on the right track, but this is how we make progress. And I think it's fun.
Yeah. Yeah, it reminds me a little. I'm always fascinated with like religious texts. Obviously, growing up religious, I'm interested in all religions, and specifically Hindu cosmology.
Mm-hmm.
I don't know if you're familiar with this or if this comes up kind of like tacitly in your research, but this idea of the yugas. The Hindus have this understanding of the conception of the universe having different yugas that all exist in different times, and that when one yuga ends, another begins, and that this is kind of extrapolated from a very sort of micro idea of like, a flower existing and then dying, but then from that death comes new flowers.
Right.
And why wouldn't the universe operate within a similar way? So they come up with this idea of the yugas. And so it's a unit of time that represents the world age. So you have the Satya, the Treta, the Dvapara, and then the Kali Yuga. And we're in the Kali Yuga now. And that prior to this universal existence, this time span of 13 billion years, 7.7.
13.77.
Sorry,
we got to be precise here.
That it was predated by another universe that ended, and that then caused this one,
or gave birth to it, or yeah, absolutely. And the idea of cycles of Big Bangs, of cycles of universes, also comes into this multiverse idea, where there's an infinity of universes, a chain of universes, one always propagating into another, where universes aren't just happening out there, but in our far distant future, there'll be some quantum process that sparks a new Big Bang. Absolutely. And right now, all those ideas are very speculative, but also very fruitful. Worth studying, worth investigating. And in physics, honestly, there are no new ideas under the sun. Right now, Big Bang cosmology is leaning a little Catholic. 100 years from now, Big Bang, cosmology might lean a little Hindu, based on more evidence in our physical understanding. The mythologies that we have created over the centuries. Humans have been creative and curious and inquisitive since we've been humans. It's part of our defining nature. And so we've come up with all of these cosmologies, all of these options for cosmologies. And in science, we are trying to match those stories, those ideas, those wonderful creative ideas with the evidence and wrap it in mathematics and be able to make predictions. And yeah, I hope 100 years from now, 200 years from now, our conceptions of the Big Bang are radically different. They would say, oh, yeah, you understood the Big Bang and it looked like your universe, and your universe from the moment of your Big Bang is 13.77 billion years old. Maybe we get a few more decimal points on there. But then there's also this other story. That was just the last chapter of a much larger book. And then now we understand the chapter that came before, or we understand the process that led to it. At the end of the day, you're always going to run into a major philosophical issue, which is, why is there something rather than nothing?
Right.
And even if you create the universe, you come up with some weird quantum mechanism to generate the universe out of nothing, then you have to explain the existence of a quantum mechanism. You have to explain the existence of the laws of physics in the first place.
Right. We have
to generate a material existence. You are always going to run into that, which is a delicious philosophical question that has bedeviled humanity for ages, and I suspect is going to cause us a lot of heartburn for many years to come, which is a wonderful place to be in for someone who enjoys curiosity.
It is a more palatable idea to me, I guess, when the idea of, or the notion of this Big Bang, and obviously the seminal question behind it of what existed prior to, I never really considered the idea of like, another universe, or the pre-universe that caused our current universe.
Some other thing.
Yeah. Right. Which I wonder, the
Multiverse.
Yeah. Is there any issue with like entropy in that regard? That if we accept that our universe will freeze out due to the loss of energy, is it possible that in that, freezing, that new energy can...
Absolutely. So there are a lot of questions about entropy and the evolution of the universe. especially since it seems like that our universe had to start in a very low entropy state, a very highly ordered, organized state, which is not mapped to our picture of the actual evolution of the Big Bang at all. So that is a major open question. Also, that relates to the potential flow of time. And then if you have these cyclical universes, like how do you like reset the entropy level of the whole entire universe? Very powerful questions, very interesting questions, absolutely. We should also keep in mind that entropy as a concept was invented in the 1800s. The guy who came up with it was Clausius, Claussiu. I don't speak German. We'll get to him. Oh, no, that's Claudius, Roman emperor.
We went too far back.
Also, our wormhole went, no, we need to go back in our wormhole. Clausius with two S's in the middle. Rudolph, there he is. Look at that chin beard.
Oh, wow.
Major chin strap beard action going on.
I am glad we left that look behind a little bit.
That's okay to leave behind.
Yeah.
Sashes, yes.
Yeah.
Chin strap beards,
he looks like a Dagestani wrestler, doesn't he? He looks like a little bit like he would like sweep in the UFC.
Yeah. So he's a German physicist who came up with our modern conceptions of entropy. Entropy was invented to explain the behavior of steam engines. In fact, all of thermodynamics and statistical mechanics, people had started inventing steam engines, and the physicists are like, wait, what are these things? We should probably understand how these things work. And then out of that came all of our theories of thermodynamics and statistical mechanics, including our conceptions of entropy. There are many arguments to be made that maybe our understanding of entropy, which is very powerful and incredibly useful, but let's remember it was designed to explain how steam engines work. Maybe on cosmological scales, when we're talking about the birth and death of entire universes, maybe this conception of entropy as we currently have it may be coming up a little bit short. But we don't know. We don't know. This is a wonderful set of questions to ask.
Yeah, it is enticing to me, this idea that the universe is eternal. Maybe I don't know why, but for me, it just like makes me feel like, okay, at least that is more coherent as an idea than that there is a beginning, but there's also a pre-beginning or something.
Yeah.
Like that is like a fundamental, kind of question for me when it comes to like the belief in some type of divinity is like, if there's a start, then what causes the start, obviously.
Yeah.
But the eternality, I guess that also requires a start in some capacity.
There needs to be the fundamental, even if you have an infinite chain of universes, you still need to explain the essential fact that there is an infinite chain of universes rather than not an infinite chain of universes.
This question of why does something exist instead of not existing,
exactly.
Which is like a deep philosophical question that I don't know if there is really an answer to.
They may not ever be an answer, and that's okay. But the overall argument that, hey, you can't have infinite chains of universes because entropy says you can't do it. And you're like, well, how do you know entropy is right? And you say, well, Chinstrap guy told me it's right. And he's going to throw down if I say no. I mean, all evidence we've acquired so far says that our understanding of entropy is correct.
Mm-hmm.
Also, we're running into these major issues when we try to address the evolution of the entire universe. So, open research question.
Yes, this is
job security.
Kalam's cosmological argument for the existence of God, I think.
Oh, I don't know if I've encountered this.
Oh my goodness. I mean, this, again, gets more to like the philosophy, sort of theistic nonsense.
Yep.
It exists outside of the material.
You said Coulomb?
Yeah, Calam.
Oh, okay. I thought you said Coulomb, like as in the French electricity guy.
Oh no, I don't.
Okay. Different guy.
I mean, yeah, Kalam. Yeah, cosmological argument.
Debunked.
Oh,
wow,
yeah.
Second.
There's a lot of discourse and debate around this idea. I actually don't know who this guy is at all. A medieval Islamic school of thought. Interesting. But basically, it's this idea that the universe had a beginning, and everything that exists has a cause. There's another version of this argument known as the contingency argument.
Okay. I have encountered the contingency argument,
which is a kind of the same thing. There's subtle differences, and I think a lot of philosophers find the contingency argument to be a little bit more compelling, that things are either contingent or necessary, and that all things that are contingent upon something else that's necessary, that might be contingent upon something else that's necessary, all the way back to the first necessary, causal agent.
But then why does that? So like my question with that, and setting aside questions of faith, and because okay, if the universe had to have a cause and you want to assign that cause to a divine agent, well, then what caused the divine agent? Now, this is where you appeal to faith and say, well, divine agents are special.
That is the ultimate necessary thing.
Okay. But then you could just as easily cut out the middleman and just say, well, the universe is the ultimate essential thing.
Which I think a lot of maybe more modern schools of spirituality would say that is the divine being, that is the entity that all things are pointed towards, is the universe, the cosmic consciousness of all things being connected, the observer that sees all things that exist. And that ultimately comes back to faith. Yeah, which, absolutely, as we've discussed before, is just kind of, you just leave it alone until there's more.
At least in terms of approaching the physical universe and trying to understand it through physical laws. This is our job. This is what we're trying to do. There are also all these questions of faith.
Right. Or I guess the other one that I think Hitchens said was the only good argument for the existence of God was the fine-tuning argument. That...
fine-tuning. Oh, fine-tuning.
What are your thoughts on the fine-tuning argument?
This universe has a lot of properties, and a lot of fundamental properties. Like the charge of the electron. Hey, there's this particle called the electron. It has this much electric charge. Okay. Could have had something else. Could have had twice. Could have had a quarter. Could have been all over the place. But no, it's every electron in the universe has this exact charge. There's the speed of light. Could have been faster, could have been slower. No, it's this speed of light. Strength of gravity. Gravity could have been stronger, could have been weaker. It's this strength. If you change any of these numbers, if you go in there with a wrench and you're like, okay, I have superpowers, and I declare by I was going to say executive order, but that's a little loaded nowadays. I declare I'm now supreme arbiter of time and space. I declare that the charge in the electron will now be twice as much as it was before. The entire universe breaks. All chemistry changes. Stars work differently or don't work at all. I'm going to make the speed of light half of its value. I'm going to do other things. I'm going to have 4 spatial dimensions. I'm sick of 3. I'm always bumping into people. I want a 4th spatial dimension. Okay, the universe just breaks. You change any of these numbers, the universe just falls apart, which means we don't exist. Oh, what do we do with that? So one answer is that these constants of nature, these properties of the universe, actually emerge from a deeper understanding of physics that we do not have yet access to, that they appear to us as constant, as something that is not evolving from some natural theory of physics. Is just the way it is. This is a sign that we do not fully understand the laws of physics. Okay. But then you run into a question again, which is, well, those laws of physics have to be those laws of physics. And if they're different laws of physics, then the universe would be different and you wouldn't exist. So no matter what, you run into issues. And the issue is the fine-tuning argument. Why are we here? Because the universe is tuned to allow us to exist, to permit the existence of conscious life as we understand it. So why is the universe tuned this way? Why is the speed of light that way? Why is the strength of gravity that way? Well, maybe there's a divine agent that did their homework, took freshman physics, figured this all out, and made it so. Made the universe this way so that we could exist inside of it. Okay. Valid argument.
But now we're back to why is there something rather than nothing?
There's that. Okay, there's that. But we can also address this. Like, okay, valid argument. There are other potential approaches to the fine-tuning argument. One I've already mentioned. We're not done in physics. So maybe we haven't figured out the deeper cause or origination of these constants. Maybe there's a reason why the speed of light has to be that value and no other value. Maybe there is. We don't know what it is, but maybe there is. So there's that line of thinking. There's also the multiverse. We can bring in the multiverse because different bubble universes can get different laws of physics. They can get different. That universe, if you bring back the multiverse image with all the bubbles, like, okay, we got this speed of light, this charge on the electron over here. Maybe in that, no, Lemaitre, get out of here. We're done with you. Yeah, like, okay, we've got our universe right there with our laws of physics and the way we understand it. But then the neighbor universe has different physics, different electron charge, different speed of light. And we find ourselves living in this universe because this universe is compatible with life, while the next door universe is not. So of course, this is what we see.
Or the next door universe has way more life.
Exactly. Or, and that's the last thread. And so this is called the anthropic principle, which is an answer to the fine-tuning argument. We find the universe to have these properties because if it didn't have these properties, we would not be here to find it in the first place.
Right.
It's not the greatest of arguments, but it is an argument. And then the last one is, well, that's our kind of life. You know, with like electrons and atomic nuclei and chemical reactions and neurons and all that. Yeah. If you radically change, like you double the speed of light, you make an extra spatial dimension, you change the strength of gravity. Yeah. The universe as we would recognize it would be obliterated and our kind of life would be impossible. But maybe we're just being really myopic about what kinds of life are possible, and that as long as you have a physics, you can have some form of consciousness emerging in it. I don't know how. Don't ask me how, because I have no idea how. But maybe, let's say you were to change the universe, brand new set of physics, or, you know, all of us are wiped away, planets dissolve, all that. But then a new kind of structure emerges. Maybe a new kind of complexity emerges. Maybe consciousness arises. And then those conscious beings sit around saying, man, could you imagine if the universe was different? We wouldn't exist and life would be impossible. And that no matter what, you end up with conscious beings sitting around saying there's no other way for the universe to even possibly exist.
That's interesting. Yeah, there is a little arrogance, perhaps, or a narcissism.
Yeah.
Like a very human, anthropic.
Like this is it.
Yeah.
Like there's no other ways for life to be possible. And like that is very short-sighted.
And I think it's also kind of limited by our understanding of our own consciousness, that it's hard for us to conceptualize a consciousness outside of the consciousness that we have because we don't even understand our own consciousness.
Yeah.
So we're trying to map what it even means to be conscious.
In our own way.
And
let alone something else's way. Yeah, exactly.
What's up, guys? We're going to take a break really quick because I'm sitting here in my beautiful tent, as you can see, every week, day in, day out. And people always ask, they say, Mark, how do I have a tent like that? I want to sit in a beautiful tent and invite a lover, a friend, someone that I appreciate and adore. I want to give them a good time inside my tent. Well, it's easy. Thanks to the good folks over at BlueChew.com. That's right. Blue Chew is the original OG brand offering chewable tablets. And what do these tablets do? Oh, I'm glad you asked. They are going to give you just a stronger, harder, and longer lasting sexual performance. That's right. They're going to help you pitch a tent any place, anywhere. And the best part, it's all done online. That means you don't have to go to a doctor's office and talk to them and be like, oh, I'm feeling some type of way. Look, this is not for people that are, lacking necessarily. This is for people that want to have the best experience of their life, whether it's Valentine's Day, birthday, a funeral. Who knows? Whenever you need it, you never know when you could use Blue Chew. And we have a special deal for the listeners of this program. That's right. Try your first month of Blue Chew for free. That's right, completely free. Mark, is it going to work for me? Is this, hey, it's free. Why not just try it? Visit BlueChew.com for more details and important safety information. And we thank Blue Chew for sponsoring this podcast. All right, now let's get after it and let's get back to the show. It's a slight deviation, but I've always questioned this when it comes to the alien hypothesis and that, and actually trying to map what aliens look like, the grays that people see in films and things like that. And I've spoken with people that have encountered, through their own accounts, aliens, that they've been abducted. They've talked about these experiences in very real terms.
Absolutely.
And the question that I've always wondered is, why are they also hominid? Why do they resemble so much of our human affect? And I'm curious your perspective as a cosmologist.
Yeah.
Is it possible that on these distant planets that they also go through the same evolution to have, eyes and a mouth and a head and sort of this, fractal kind of human development pattern that we have?
We honestly don't know what forms alien life might take. That's assuming alien life even exists. Maybe we are alone. There are very solid arguments to be made that intelligent life, especially, is going to be rather generic. Because if you look at what we're made of, fundamentally, oxygen, hydrogen, carbon. Oh, look, it's the most common elements in the universe. Got it. How are they combining? Oh, super generic. Okay, once you get life moving, you need to acquire energy. You need food. Where is life going to appear? It's probably going to appear on the surface of a planet. It needs access to water. It needs a solvent. There's only so many ways to build structures that are stable and can build off of themselves. You need a lot of carbon. You end up needing a skeleton. Oh, you need to interact with your environment. So you need grabby things. You need to move around. So you need locomotion. There's only so many ways to achieve locomotion with a physical object. You need to process a whole lot of information. There's a lot of information. There's pressure waves coming at you. There's electromagnetic radiation. There's temperature. Oh, it makes sense to have a central cluster of information processing that's handling all the sensory input and sending out commands so that you can grab your food and you can escape predators. And it makes sense to have that all centrally located. So you're probably going to have something like a head that does a lot of the sensory input and command infrastructure, and that at the end of the day, you end up an intelligent creature ends up looking pretty much the same as us. I call this the Star Trek hypothesis. They got an extra forehead wrinkle.
Yeah.
Okay, you can poke holes in that argument all day long, but it is an argument. The counter to that is have you seen life on Earth and the weird stuff that, especially ancient life, the weird body plans, the weird arrangements of sensory organs and mobility and motility? Man, there's a million different paths that evolution, which is undirected and does not have a goal, but any one of those, just by sheer luck, could have ended up with intelligent creatures. And then, well, that's assuming that life has to have the same chemical basis as us. Yes, we use water as a solvent, but hey, there are liquid methane lakes over there on Titan orbiting Saturn. Maybe that can be a home for life that has a completely different biomolecular basis than we do. And then you can just go nuts and say, well, hey, maybe consciousness, intelligence is some more abstract things. Maybe there are dark matter creatures that are invisible to us and we're invisible to them, that are able to form complex arrangements that can appear, that can act and have agency and make decisions in ways that we can't even imagine, because we are so tied to our own genetic heritage and our evolution of life on Earth. And that, man, this is purely me. This is not based on anything. This is just fun stuff I like to think about. I imagine sometimes, I look out at the stars and I wonder, are we looking at intelligence right now and not even recognizing it for what it is? We have no need to explain anything we observe through the actions of any intelligent beings. That's not where the argument is going. It's just, are there conscious entities out there that we don't even, that we have so many biases wired into our DNA that we can't see them for what they are? It's just a fun thought to have.
But also, how could we look for them? Right? Like, if we don't even understand what our own consciousness is.
Exactly, which is why most searches for life focus on life like our own, because we know what we're looking for.
Of course, and that's the only thing you could look for.
And it limits our ability. It sure does. It cuts out a lot of potential options, but it increases the chances of success.
Yeah. It's, again, one of these questions, like, another like philosophical religious question that I struggle with is this idea of, like, why would God, if there is a God, why would God create planets that have nothing on them? Why would he create rooms that you don't furnish? Like, why do these things exist even? I've envisioned, like, if I just landed on one of these planets, it would just be such a bizarre experience to be so isolated. There's nothing there.
Pull up the rover images from the lander images from Titan, the Huygens probe, Huygens, because Huygens was a guy, and we named the lander. Look at that. The right-hand image, that is from the surface, the one with the rocks right there. That is the surface of a moon of Saturn.
Yeah, this bothers me. I don't like looking at these images. Genuinely, it is unsettling.
Or
to
the
me.
Mars rover images.
I don't like
just
any of
these
it.
vast.
I don't like any of it. Like the idea, like there is a daytime and a nighttime, and that there's Christmas happens here. You know what I mean? Like, just the idea that, like, time is still existing in these places, and, like, wind. Is there a wind? There's an atmospheric movement.
Like, Mars has been existing and doing its Martian thing for billions of years before we came around to take some pictures.
I don't like it one bit. It bothers me that this just is there in the same way that the Sahara Desert is there, and that it's just for nothing, and it freaks me out.
Is it for our delight?
But we couldn't even delight in it until 50 years ago.
It took us a little bit of time, but we got there. All right.
Yes. It gives me this unsettling feeling where I'm like, why is it there? Genuinely, I don't know if I mentioned this to you. I smoked weed maybe 20 times in my life. Okay. I can't smoke weed anymore because every time I smoke weed, I think about planets.
Oh, and it's too much.
It genuinely bugs me out. Where I go, there's so many of them, just like this one. That just, and by this one I mean Mars, that are just there for no reason, for no apparent reason. And it bothers me a lot.
Well, are you here for a reason?
I mean, I would like to think so.
Okay, we'd like to think so, but that's a very egoist perspective.
Yeah, of course.
Mars, stupid Mars, it doesn't have a reason, but Earth totally has a reason. I know this contradicts my entire essay about New York Times, but like that's the counter to is, well, what makes us so special?
Right. Yeah.
It's just because we have eyes and we get to look around.
Yeah. Consciousness, I guess. Yeah. And have you heard of this idea of panpsychism?
Yes, I have.
By David Chalmers, I think is the first person to propose this. And I know a lot of people within the consciousness philosophy space dispute it. And I also have no real bearing for why it is the case. I also have a very loose understanding of how it works. But this idea that, like, molecules on an atomic level, little atoms can possess this very, very loose, sort of unstructured
piece of consciousness
that when assembled into complex shapes, that then could possess consciousness at scale the way we understand it.
I mean, it's a very appealing and intriguing idea because, like, I hold this water bottle and I'm like, I'm pretty sure you're not conscious. And I look at you and I say, I'm pretty sure you are conscious. And then I look at, like, a dog. I'm like, oh, you seem a little bit conscious.
More conscious than that.
Definitely more conscious than the bottle. Definitely less conscious than you.
Some folks.
But like a little. Like, you got a little personality and you seem to interact with the world and you seem to make your own choices. So there does appear to be a spectrum of consciousness, or some vague, using some vague definition of consciousness, because good luck, defining consciousness. But there does seem to be a spectrum. So it's a valid question. Where does the spectrum stop? Does it stop at a dog? Does it stop at a bacterium? Does it stop at an atom? Does it stop at a like where's the line? Is it nothing, 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 and then you start ramping up in terms of consciousness, which also leads to the question: is this it?
Or is there more?
Or is that like the way we look at a dog and say that you're so cute, you're kind of conscious. You're just like a little bit sentient, just enough to be adorable. Is there some alien species looking at us saying, look at those creatures, they have this much consciousness? Or is it nothing, 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 then rising, and then this is it? Like as soon as you're like self-aware in the same way we are, sentient in the same way we are, does every alien creature in the universe, once we reach this, there's a plateau?
Who's to say?
Who's to say? David Chalmers.
Yeah, I
That's
guess.
who's to say.
Yeah. But I don't know. I sometimes look at these planets and I'm like, I wonder if in the way that I can look at a tree and we're talking about that spectrum of consciousness, I'm like, all right, maybe it's more conscious than like a rock.
Yeah.
Because it's growing,
maybe.
it's like it has like this.
Seems to make choices.
Yeah, it's kind of moving towards the sun. There's kind of like a cause and effect that's going on.
Yeah, send chemical messengers out. It interprets the world in a way and reacts to that. Is that a little bit conscious? It's a fun and delightful. I don't want anyone to think I am not an expert on this at all. These are just my own personal musings.
Sure.
I'm not speaking in the capacity of my office.
Yeah, this is Paul the guy.
Paul the dude.
Yeah.
Not Paul the cosmologist who enjoys thinking about these exact same kinds of questions.
Yeah, I don't know. It bothers me, and I wish that I had more of a grasp on it.
I think most people do.
Yeah, is it unsettling for you? I know we talked about it a little bit, that you kind of just choose to accept things, on the basis that it makes you feel good, this idea of free will, which I think all people do.
Ultimately, yeah.
But are there questions in this same vein that make you lose sleep?
There are many questions that make me lose sleep. Most of those questions are personal. Like, am I being a good parent?
Sure.
Am I being a good person? How do I take care of my family? Those everyday issues. Man, what do I do? My car got in a wreck. Like that's what keeps me up most nights, are like mundane issues or of the issues of daily life. The big philosophical stuff, I don't pretend to even be on an approach to an answer to those questions. My own research in cosmology is much narrower.
Mm-hmm.
I delight in studying cosmic voids. I delight in studying the universe. I delight in finding connections between the universe and our own humanity. Other questions about the ultimate fate of the universe, I enjoy reading about ideas and I react to those ideas. I think, okay, this idea is totally stupid. This person is a moron. How did they get a faculty position? And then like this, this idea seems pretty promising, but that's just based on my own personal biases and opinions and upbringing, not based on the weight of evidence or the strength of the philosophical argument. I don't think we live in a simulation, but that's based on, I don't think the simulation argument is very strong. But that's just me, saying it in front of a microphone. That's not based on anything stronger. I have no published counter to the simulation argument. But what drew me to cosmology, what drew me to this field, was being drawn by the night sky. Getting to sit out there. I live in Connecticut. I don't have a great night sky. I grew up with one in the Midwest. Anytime I travel, especially to the desert, any desert, I go out there and I will spend hours asking these same kind of questions and just letting my mind wander. And it's that delight in the wonder that empowers me every day as a scientist and as a science communicator.
I love that, genuinely. This is one of the reasons I love talking to you about these kinds of topics, is that we get to muse and I get to ask my dumb questions. You can kind of refocus me.
Not my dumb answers.
Not the dumb answers. You're able to be like, all right, you're off the rails. But you have just a great capacity for communicating these kinds of topics to the public, which is the last thing I want to ask you. How can we rebuild the public trust in science as a whole?
This is... the past couple months have been a very scary time to be a scientist. I'm personally I will say at the outset, the actions of the administration and Donald Trump and people like Elon Musk, they haven't personally affected me. My own research lines are very slim. I do not have a lot of funding. Those are pretty secure. I spend most of my time. In fact, as a science communicator, business is booming. People are wanting my opinion a lot about what's going on. I have a lot of friends and a lot of colleagues who are having to radically reshape their lives. I was just visiting an old colleague of mine, and he's here on an H-1B visa as a researcher, as a scientist. He's a brilliant, brilliant cosmologist. And he's wondering, with all the discussions that have happened and continue to happen over immigrations and the status of H-1B visas and, how many should we have? Should they be revoked? He's like, what does my future in my career look like? I have many colleagues who have had to rescind offers to graduate students because now their funding is very uncertain or have been outright pulled back. Most of my research has been publicly funded. As a cosmologist, almost all fundamental cosmology research is either funded by the National Science Foundation, by NASA, or the Department of Energy. The National Science Foundation has circulated a memo. They are expecting a 2/3 cut to their budget, which would completely destroy fundamental research in the United States. NASA has just circulated a memo to the Science Mission Directorate. This is the funding arm for fundamental science in NASA. They've put a pause on most. There's a major, major annual grant program called ROSES. I totally forget what it stands for. Research Opportunities, Space, something, yay, exciting. It comes out, the solicitation comes out on Valentine's Day every year.
That's cute.
They pause that for the indefinite future because they don't know how things are going to change. And so a lot of researchers, a lot of graduate students are seeing their futures uncertain now. They've been accepted to graduate school, and now that their offer has been rescinded. Early career researchers who are just trying to get tenure, if they don't get grants, they have no future in academia. It's a very scary time. Sadly, I predicted this. I did not want to be a predictor of this, but I had a book come out last year, about almost exactly 1 year ago, called Rescuing Science, Restoring Trust in an Age of Doubt, which laid out how science, the relationship between science and the public has been breaking down over the past really 20 years, but then accelerated by the coronavirus pandemic. And not just cosmology, not just astronomy, not just physics, but all fields of science are suffering. And that for decades, science enjoyed broad, bipartisan congressional support, broad, bipartisan public support, where generally people said, yay science, yay funding for science, let's keep doing it. You're doing a great job, everyone. Keep doing that sciencey thing that you're doing. And generally, there I am on David Kipping's podcast talking about this book.
Oh, nice.
Wow, that's very circular.
Yeah, isn't that great?
And over the past 20 years, that relationship has been changing. Science has been the topic of funding science, supporting science, and trusting science has started to become polarized, where generally more Democrats or liberal-leaning or Democrat-identifying people supported science more generally than Republican-leaning people did. And scientists did absolutely nothing about this. You can see the data, you can see the opinion polls, you can see the funding, which has been flat or declining, slowly declining for 20 years. And scientists, this is why I don't get invited to a lot of parties. Scientists didn't do anything. which is scary to think about, that academics, scientists across all fields, some of the smartest human beings on the planet, saw the erosion of trust in what they were doing before the various, saw this polarization happening, and made no attempts to reach across the aisle, to engage, to explain the value. Like, most fundamental research in science is publicly funded. It means it's funded by the taxpayer. We exist at the pleasure of the taxpayer. Scientists as a group did not recognize that basic fact, or acknowledge, or just assumed that we would always have broad bipartisan support. So in my book, I said, a reckoning is about to happen. And we're making it worse because we are refusing to engage with the public. Most scientists do not communicate with the public at all. And in fact, if you do it too much, it's a detriment to your research career. We refuse to engage in politics. If you talk to an average scientist, you pluck them out of a random university and say, hey, what are your thoughts? They'll be like, oh no, I'm not touching politics.
Mm-hmm.
They have their private thoughts. They'll vote, but they're like, I'm not going to talk about. But like, if your research is publicly funded, you are by default a political creature. And your refusal to engage with lawmakers on both sides of the aisle to convince them of your value is going to come at you. Or, as we've seen over the past few years, if you align the identity of science with liberalism, with democratic side of the political spectrum, that's going to hurt you. And I wrote in the book, Democrats are only in charge roughly half the time. And if we only receive congressional executive support for funding science half the time, science is going to go away. We've also made some serious mistakes as scientists, as a community. We've let publishing go out of control. We publish way too much. We are drowning in publications. We have let peer review not do its job because we're publishing too much. We've let fraud rise. The levels of fraud now in scientific publications is out of control. There's deliberate fraud. There's, faking data. But then there's also sloppy mistakes, laziness, obfuscating analytical routes to get a preconceived result.
Perverse incentive structure, maybe.
Perverse incentive structures, exactly, within academia. And the book is highly critical of that side. Like, we've made choices as a community to make people not trust us. We've allowed fraud to go unchecked. We've allowed publications to flood things where no one knows like what's authoritative and what's not authoritative. We've refused to engage with the public as a community to explain our value and what we do and what we provide to you, the taxpayer. Like, this is what you're paying for. Look at all the amazing things. Maybe it's advances in technologies. Maybe it's just, the world is a more beautiful place because we understand more about the Big Bang. But like, that has value, and we've failed at communicating that value. And what I am seeing now is it is heartbreaking. But I also saw it coming, which is an unfortunate position to be in. And I am scared to see what the congressional budget process turns out over the next few months. I'm scared to see what the NSF budgets are going to be, what the NIH budgets are going to be, what NASA's, whatever the heck is going to happen to NASA, especially when it comes to fundamental research. I'm scared, but also I don't blame people for not trusting science. I don't blame people for thinking it's a waste of money. I don't blame people for wanting to see less money spent on scientific research, even though as a fraction of the total federal budget, we spend nothing on science. NSF is less than 0.1%, 0.1% of the federal budget. It's all of NSF. All of cosmology and astronomy in the United States is funded on just astronomy, something like 0.01% of the federal budget. Gets us all of astronomy and cosmology. It's rounding errors. You know, if you root around the couch cushions of the Pentagon, you'd come up with enough money to fund astronomy for decades, you know, something ridiculous like that. But I understand why it became a target, because people stopped trusting science and stopped seeing the value in science, especially amongst Republicans and right-leaning ideologies. And if you don't trust something, if you don't see the value in it, of course you don't want to spend your taxpayer money on it. You'd rather that money go somewhere else or go nowhere at all, so there's more money in your pocket. Of course. I think scientists have a large share of the blame, if not most of the blame, because we created the conditions for people to not trust us, because we arrogantly assumed that people would just always trust us and always fund us. And that's not true. And that came to light with the coronavirus pandemic.
Yeah. Even just considering my conservative family and friends, I think there's a feeling that, science is sort of an elitist practice, that it exists within, like Ivy League laboratories, and that's where it's done, and that it can be used as a weapon against them by politicians, maybe acting in bad faith or maybe just negligently with what the science, is available. And specifically during COVID, I think was a major turning point.
Absolutely.
Where there's many people that were like, okay, we got to distance this far and the science says we have to do this, or I have to get this vaccine because the science says so, or else I lose my job.
Yeah.
And that there was a real feeling of, a loss of autonomy, and perhaps the science was correct, or perhaps it was incomplete, but then politically utilized in order to push something. Or maybe it was just a bunch of people acting in fear, trying to do what they thought was best with what was available at the time.
Or maybe all of the above.
Precisely. And I think those conditions really create a lot of uncertainty and distrust amongst specific subsets of the population.
Absolutely. Absolutely. And that's exactly what I addressed in the book. Like, science is an elite institution. It took me 11 years to get my PhD. It took me 5 to get a bachelor's and 6 to get a PhD. I recognize the enormous amount of privilege. Like, my parents, they were totally solid middle class. I grew up in the middle of nowhere, Ohio, like an hour outside of Columbus. My dad was an accountant for the Defense Department. My mom was a real estate agent. I was able to get on a track to go to a good college for undergraduate and pursue a PhD. It takes an enormous amount of privilege and position to be able to even have that path open to me. And it takes a lot of work. And I do hang around Ivy League institutions and other institutions of excellent caliber with beautiful quads and old stone buildings. And yeah, it's totally elite. Scientists are a part of the intellectual elite. I'm not speaking personally. I would never do that. But scientists as a class of people are among the intellectual elite of any country and of the world. We are part of the decision makers and influencers. And scientists don't acknowledge that. They don't recognize that. They say, oh, no, I'm not getting involved in politics. I'm not going to talk about politics. I'm not going to talk to lawmakers. I'm not going to talk to people. And that choice to isolate themselves in the ivory tower is a disastrous one, because it sets up the conditions, because scientists aren't trained to work with politicians. They aren't trained to communicate, to work with media. They aren't trained to communicate with the public. They end up getting used. Scientists with very good intentions have no idea how to communicate the impact, importance of their work, and the nuances of their work. Science is all about nuance. They have no idea how to communicate that to the public. And then there are bad actors. There are scientists who are evil. who use their powers for bad ends.
Mm-hmm.
And know how to work the media system, know how to work politicians, and work with them to achieve their own disingenuous ends. And there's nothing within the scientific academic community to address that, to counter it, to put good people with good intentions in the right places at the right times so that they can give an honest accounting of the scientific evidence and the viewpoints of the broader scientific community. We do a terrible job at it. And so we end up with the conditions where bad science actors are out there and there is no effective counter to them. And there are well-intentioned scientists who have no idea how political machines work, who have no idea how the media works, who have no idea how to communicate the value and importance of science, of what they're doing, whether it's disease research or cosmology or anything in between. And you end up with a politicization of science, where science becomes yet another political tool to hammer your opponents with, yet another talking point. And the whole point, the whole intention was that science is supposed to sit outside of that, where we're here to understand how the universe works. Sometimes we create some fantastic technology, but we're here to study and explore and understand and create, and then we give it to you, to humanity, to the public, to political leaders, to industry, to do with it, to make the world a better place. That was the deal made in the post-World War II era. But that's not the deal anymore.
So how do we fix it?
One is, it's going to have to be a generational change. I've given a lot of talks to my colleagues at departments, universities around the country over the past year. Some of them, I'd say about half, don't even want me to come. I will say, hey, I'll reach out to one of my colleagues or email someone in some department, say, hey, I wrote this book and I'd love to talk to your department about it. And they'll say, oh, no, it's not we only do technical topics. If you're not, you can come talk to us about your research on cosmic void, sure, but not this. So about half don't even want me to speak. And then when the audiences who do want me there, they're very receptive. They're very warm. They understand. They get it. The recommendations I have are, one, we need to radically alter our publishing paradigm. Last year alone, there were 5.1 million published papers across all of science, across the world, so it's going to be a large number, but 5.1 million research papers. It's too much. We're publishing too much. We're putting too much demands on ourselves, on our students, to publish. This is leading to sloppy results. This is leading to inconsistent results. This is leading to unproductive, unverifiable, non-reproducible results. It's leading to outright fraud. So number one, we need to clamp down on publishing. We need to lower the pressure. We need to lower the stakes so that we can give individual scientists and groups more time to come up with a solid idea. We need to not just encourage, but enforce our scientists to speak to the public and to lawmakers. We need to give them training, science communication training, media training, politics training, maybe a little political science course here and there wouldn't hurt, as part of their standard procedure for training new scientists, as part of undergraduate, as part of graduate school. Because for a scientist to exist in the modern world, we can no longer assume that we will have broad bipartisan support. It's manifesting right now. The outcome of that thought that we can just sit back and just assume we'll always be funded. Guess what? It's not true. When we're feeling it right now, most scientists just assume that Kamala Harris would get elected.
Mm-hmm.
And she didn't. Here we are.
Mm-hmm.
We can't make that assumption anymore. And we can't just rely on Democrats or the Democratic Party to support science anymore. We can't just communicate to the public. We have to deliberately reach out to the right wing side of the country, of the political spectrum. We have to reach out to Republicans, to conservatives, to people in the middle, people who didn't vote at all. We need to find ways to communicate our value to them, the value of what we're doing, to justify even 0.1% of the budget. We need to justify that 0.1%.
Mm.
We exist at the pleasure of the public.
Yeah.
I get to study cosmic voids because the American people have decided that that's worth a fraction, it's tiny, tiny fraction of a fraction of their fortunes. And for that, I'm forever grateful and forever privileged and forever dedicated to communicating science to the public, because it's owned by the public. It's yours. It's all of ours. As scientists, most scientists do not recognize that. Or they're too busy just trying to survive.
Yeah.
So we need to radically reshape internally how we deal with fraud in publication to make ourselves more trustworthy. We need a lot of training in dealing with the public, and with politicians, and with the media. And then we need to go out there. Tell people why it's worth it, why the NSF is worth keeping around, why the NIH, NASA, Department of Energy, why it's all worth it. Even if it's a tiny, tiny fraction of the budget, we need to justify it.
And that's why I love your work. Genuinely. I like watching it. Like, I like going through your YouTube channel and being like, oh, this is an interesting question. And it's also made for me. You know what I mean? Like, it's made for just like an average dumb guy that's able to watch something and like, chew on a question that's interesting. It takes it out of these Ivy League, like closed door, communities, and just democratizes it for all people. And it requires a lot of humility. I think the fact that someone like you that has spent, what do you say, 11 years getting a PhD, and, an extra 20 years that's just discussing these ideas within, specific communities, now to come to me and sit in my tent and explain these concepts to me and, have a real human conversation, I think says a lot about you and your character and your dedication to furthering science communication.
Thank you for that. That does mean a lot. What I want is to put myself out of a job. That'd be my ideal scenario, where there's so many scientists out there communicating so much to the public so that the public understands the nuance of science, the complexity of science. The real world is messy. That's why we need experts, elite experts to dive into the workings of the natural world, because it's really hard. It's super complicated. It's messy. And we should never position science to give black and white yes or no answers, because that's not how the world is. And we need to communicate that. We need more scientists out there communicating more about the complexity and nuance and beauty of the world, and digging into the gray areas so that people understand that this is the world that scientists operate in. And doing it so much and so frequently that when people have questions, they don't ask me, because there are a dozen, 100, 1,000 other options for them to ask. And then I'm out of a job. And then maybe I can retire, or like I go do something else with my life. Maybe I train them in science communication. I don't know. I'll figure it out. But my wish is that so many scientists are doing science communication that science communicator is no longer a job title.
Mm. Yeah, you exist in this sort of unique space where you're willing to obviously talk about your expertise, but also the research of your colleagues, and even, indulge me on some of the more broad, esoteric, philosophical questions. But ideally, yeah, there is a world where there are, thousands of Paul Sutters that are all, communicating with the same fervor.
Where if you have questions about voids, happy to help you out. Also, the 6 other people in the world that work on voids, you can talk to them too. But if you have a question about something else, you got someone in your back pocket, on your phone contact list, that's out there, that's already known. Like, we need to be out there as a scientific community because it's going to sound so cheesy. We need people to fall in love with science again.
Mm-hmm.
It's like the only way through this.
Yeah, it's shocking to me. Maybe it shouldn't be shocking, but it is frustrating at times that there are many people that I will reach out to. There'll be researchers within, specific areas of cosmology. I'll go through, university faculty sites, and I'll find someone that maybe did a speech that has 100 views on YouTube, and they have a really interesting field of study. And I read one of their papers, and I go, oh, wow, this guy is awesome. Like, this guy's a star. He's got really interesting information. And I'll reach out, and they'll respond and say, oh, I don't really do stuff like this.
And you're welcome to slap them. And if they say, why you slap me, say, Paul Sutter. He said I could slap you. He gave me permission.
And on the one hand, I'm like, I get it. Your job is to do this, and you're maybe afraid of going on a platform.
Absolutely.
And you don't know me. You don't know my agenda. Maybe I'm going to try to skewer you with some type of political, leaning that you're not, equipped for. Or maybe you get nervous on camera, which is understandable. Yeah. But on the other hand, I'm like, I know you live, 20 minutes away from the studio, and I will get you an Uber. And if you don't like the conversation, we will never put it out. And I'm not attempting to get you, and I'm genuinely having a good faith convo. And also, the people I'm talking to are much smarter than me. So if they wanted to steer this whole thing and be like, actually, you're an idiot,
outmaneuver you,
very easy. It'd be very, very easy. And I'm surprised at the frequent resistance from people that are experts in their field to not want to share their ideas with someone that's eager and excited.
It's when I first started really growing my presence in science communication, I was in the middle of my second postdoc. A postdoc is a temporary research appointment after your PhD, hence postdoc, but before you're considered matured and aged enough for a faculty position. You do these like short-term research stints. And it was in the middle of the second one that I realized, A, there are no jobs, and B, that I really liked science communication. I really liked working with the public. And as I started doing it more and more, I was doing less and less research. My publishing rate was starting to go down and my public appearances were starting to go up. I would have people stop me in the hallway, faculty, at the university where I was, and say, you got to cut it out, Paul. You got to stop. You're not going to get a faculty position if you keep doing this. Turns out there are no jobs anyway, so I don't know what imaginary faculty positions they were talking about, but like but they had no idea. Yeah.
I guess
it's sad.
It's an antiquated, perhaps old school way of looking at academia, that we exist in a new time and place where ideas are more accessible for those that are willing to, make them such. And that's why I'm just grateful for you and your message and your work. And
I appreciate you giving me a chance to share some of these views.
Of course, open door, genuinely. Anytime you have something, even a paper or a book or something that you're really excited to talk about, I would love to sit down and chat with you. Beyond your intellect and ability to communicate it, just your essence and your soul, I find very charming, and just there's a calm peacefulness to it that I think is very approachable. So
I deeply appreciate that and this chance. These are always wonderful conversations, and these are my wife's favorite interviews.
Oh, really?
I do. All the interviews I've done in the past year, and this is my wife's favorite.
Oh, wonderful. Well, I hope this
or not this specific one, but the last one we did.
This one also will be the new favorite.
This will be the new favorite.
Yeah, absolutely. And shout out to your wife, by the way,
who's so brilliant.
Yeah.
Oh my gosh, you think I'm like say interesting things? Like, oh my gosh. So she's a modern dance choreographer. There are many reasons why I find her so attractive, and one of those is the way she looks at the world and the way she speaks about the world and the beauty that she creates in the world.
Well, next time you come back, bring her. We can.
We could do a double interview.
Yeah, absolutely, that'd be great.
No, we're doing that. We're definitely doing that.
Oh
my gosh,
we're just going to delve into your personal lives. Really, we're going to talk about how you met. What she sees in you. Which
I don't know. We can edit that part out.
Did you have hair when you guys met?
No.
Oh, wow.
I've been bald since I was 20.
Oh, really?
I shaved my head. I was on a study abroad trip, which was part of the university where I went to undergrad, California Polytechnic State University, Central Coast of California, had a partnership with California Maritime Academy where they train merchant marine seamen. And they had a partnership where we could join their training ship for 3 months on their training cruise. And it was my first time crossing the equator. And there's the equator cut where they shave just like a line down your head. But I did a mohawk instead. And of course, that was against the uniform rules of the merchant marine. So I had a mohawk for about 20 hours and I just shaved it off. And I'm like, oh, I was already had like a widow's peak going on, even though I was 20. I was like, oh, bald is kind of beautiful.
You got a good head for it. I'll be honest. Sometimes you see folks that are bald and you go, you could admit, it might be worth going to Turkey.
Yeah, you thought about it to pay. Yeah.
Yeah. But this,
no, I was like, I like the dome.
You shower fast, probably. Yeah.
You know, the weirdest thing for those of you who are not bald, speaking of showers, the weirdest sensation, one of the weirdest sensations in my life was the first time taking a shower as a bald human being. Just like, cause you felt the droplets. Now I love it. It's like a little scalp massage, but I was like, I was very thrown off.
Yeah. I mean, my long noodles, it'll take me 30 minutes just to comb it. It's a nightmare. Okay. Think about how much smarter I could be if I was you. I think that's probably why you got a PhD.
Well, it's because my brain kept growing and then it pushed out the roots of the hair and like because they're needing more.
And then you save time not sitting in the shower, conditioning nonstop.
No. So it's actually the opposite. So I have personally not ever done this, but I have had friends and colleagues who, I can't believe I'm saying this. Do you want the dirty secrets of how science actually operates? They bring erasable markers into the shower because you have a glass door. And shower thoughts. It's a real thing. You're taking a shower, you're thinking about work, and you get some crazy idea or like some insight, you want to work it out mathematically. So you got your shower markers right there. I'm not making this up.
This is a great idea.
You got your shower markers right there, and you start, putting some equations down. Looking at this, see if that works or that's a potential solution. It's a real thing.
Have you done this?
No, I swear, I do not bring markers into the shower, but I do take oddly long showers because I do get lost in thought. Yeah. That's super.
No phone buzzing at you. No, there's a time where you're not reachable.
Exactly.
Which I think is good.
Yeah. Everyone needs to have an unreachable space.
Yeah. Well, that's wonderful. Paul, I appreciate you so much. Thank you again for coming down and chatting with me. And let's not wait another year and a half. Let's do this sooner.
Let's do it sooner. And I'll bring Kate. Yeah, sure.
That'd be great.
Yeah.
I'll see you then. If you've made it to the end of this episode, that's because you rock with us. And for that, we rock with you. You are sophisticated. You enjoy honest, true communication, a highbrow type of person that understands this. History is not just dates and names. It is a tapestry of human triumph and tragedy. From the day Nostradamus made his first prophecy to the morning Paul Revere took his midnight ride, from ancient oracles to modern revolutionaries. That is why I need you. If you have not already, please sign up for Today in History, our free newsletter. Today in History brings you the stories that matter, the moments that changed everything, and the secrets hidden in time. Join thousands of history enthusiasts who get their daily journey through time. Don't let another day of history pass you by. Take the conversation to your inbox. Sign up now through the QR code or link in the description. Today in History, because history's stories shape tomorrow's world. Thank you for watching the episode. We'll see you next time.